Hey guys, how's it going? Welcome to another episode of Ferris Makes Demos. Just like last week, this time I don't actually plan to make anything, but I do want to go over some of the tools that we're using to make demos these days, and just generally, I guess, how our stuff works. So last week, went over Wavesaber, which is my Group Logic Coma's 64K synth. This week I want to talk about Demotivation, which is kind of the rest of our tooling, basically, for PC 64Ks. So it should be pretty fun. Again, like last week, I'm also not that prepared, but the idea is that let's throw up the tools and let's talk about it. And I'm sure there'll be a lot of questions along the way. There's a lot of little bits here, but generally it shouldn't be too terribly tough to go through. So I think this will be fun. Try Later, New School, Soda Design, Dark Second, John Hunter, Sakes, and Alkama. How's it going, guys? Good to see you again. So I guess I should start by talking a bit about kind of the scope of these tools. Basically, last week, like I said, I went over the synth, which goes over like generating the music in real time while the demo is actually playing, and it also goes over a lot of the content creation for actually making the music that's going to be played back in a 64K intro. So that's kind of the audio side, and then this is kind of the visual side. And there's kind of a lot to show here. Basically, what I have up here is just kind of some test project. Don't worry about what it is; doesn't matter. But just to kind of show you, I guess, what it's like to work with these tools. There's going to be a bit of context for why this is designed this way, and a lot of details about sort of how the data is, like what we work with when we're making a demo, and then how that gets packed up into the intro. And there's, a lot of stuff, but I hope to just kind of dig in and, show you guys a bunch of that stuff. Oh, Kama, where'd you go skiing? That sounds cool. So I guess I can just start. How do I dive into this? Probably should have thought about this a little more before I push the go button, especially because I was ready like a half an hour early, or ready. So how do I want to go about this? I guess I can just show you kind of generally what we work with. So up top here we have the viewport, which basically shows what the demo is going to look like. Let me move around some windows here so you can also see the sync tracker that we're using. I'll move this over here. Now, because my screen real estate is a bit low, these tools have not really been optimized for 1080p workflow. They've been optimized for my 4K workflow. So might have to move stuff around a lot to actually sort of accurately kind of show what's going on here. But generally, up top here is the viewport. Beneath this is the operator editor. So each one of these little boxes here is an operator. And oops, double click there. And the idea behind this is that this is basically a sort of visual programming language that will comprise the CPU side of the code that is executed every frame that actually makes these visuals that you see up here. On the right over here, then we have a sync tracker, which allows us to move back and forward in time. We can also play and stop. That's probably a bit loud. But yeah, so this is generally where we're working with things. So this is kind of mainly what I'm usually using when we're doing demos, at least the visuals. But then the other thing, of course, is a text editor, which is usually Sublime Text or Emacs if I'm on OS X. And that, of course, looks how you might expect. And over here, we're basically writing a lot of shaders, which are bits of GPU code. What should I dive into here? Because there's a lot of little pieces of this kind of thing, but I guess I could just kind of show you the different kinds of things we can do. So for example, this scene here, this is drawn using ray marching, which is just one of the many techniques you can use to draw things. It's not what we used in Elysian, but it's what we used in Migraine, which I showed last week. And I will not comment on what techniques we're using for the revision thing yet. But the idea is that generally we have some way of drawing some kind of geometry. And then we have, after that is all drawn, we have this big post-process pipeline, which is a bit of what's down here. This project right here is extremely minimal just because it basically only has one scene, which I believe is this, which is basically drawing a quad and then a bunch of parameters to the shader above that. But then the post-processing stuff is a lot of stuff. It's basically the same post-processing pipeline that was in Elysian, but modified a bit to work nicely with this ray marching stuff rather than the polygon stuff that we used in that demo. Vernbode's badge. I got lost at Java. Yeah. I should probably mention kind of what we built these tools. So these tools are custom built and they're specifically made for producing 64K intros. The tool on the left, again, which is the part that we call Demotivation, that's like our stuff. The part on the right is a sync tracker for something called Rocket. Rocket is made by Kuzma of Excess and I believe Scribble. And yeah, it has different parts of things, but like I don't think we actually use any code from the original Rocket. It's basically like a data format and kind of a protocol that you follow to do sync stuff. But then this particular editor for that is done by Emoon of TBL or Daniel Collin in the chat usually. And yeah, these kind of talk back and forth via just basic IPC. Yeah. I can explain more details there as we kind of dive into things. This whole tool is built in mostly Rust, but there's a GUI layer on top that's made with C++ and cross-platform GUI toolkit called Qt. There isn't, I guess I'll say a lot more about the specifics there. And then, of course, when we're doing visuals, we work in this visual programming language down here. And I'll get to why I kind of call that a visual programming language as we kind of dive into what these different operators kind of mean, and then how that ends up going into an actual intro. So we work with that, and then we work with OpenGL shading language, or GLSL, to actually do some of these visuals. So it's, yeah, it's pretty nice. Also, there's like, you'll notice that this tool doesn't look that great. Like there's not a lot of things here, and that's just because of my kind of philosophy with this stuff is like make it dark, get it out of the way. This is meant to be a helpful tool to make intros, not something that looks super great or that's super professional. Although I did spend a lot of time making this very stable. So even though it doesn't look that great, it is basically rock solid. And as I say that, I'm pretty sure this is going to crash during the stream, but we'll see. It probably won't, but you never know. Anyway. So this, before I get into kind of the details of how this works, I should probably just explain like what all of this is. So this operator graph, also Dark Second said, did you dive into Vulkan yet? No, haven't really done anything with Vulkan yet. We're still using GL for this. New school, it's not a real live demo if it doesn't crash. Right? All demos have to crash, at least on escape. So this graph of operators, this was inspired by a couple different tools. The older Farbausch tools from like the late 90s and early 2000s. But that was kind of an indirect inspiration. This was more directly inspired by Looney's 4K tool, which I don't know if they actually have a name for that tool. But yeah, that was kind of inspired by the Farbausch tools, and then we were inspired by that sort of indirectly. I had a different version of this where I wasn't making scenes using this kind of workflow, but instead I had like a tree view of these little, like to make a graph of things to show, basically a scene graph. And then I would make some custom operators or like custom nodes in that scene graph to actually do drawing and everything. But I found that especially with Rust recompile times not being very fast at all, and like adding a lot of those, it was a really tedious workflow, and changing anything on the CPU side was particularly annoying, especially if I was just changing like buffer formats and stuff. So that workflow didn't really work. So we needed a way to do CPU code that was a bit lower level, so that we could basically never recompile the tool while we're working with it. And then this is what after speaking with Blueberry a lot about how their tool was working, I figured I'd basically adopt their approach, but then of course extend it for 64K. So it has a lot more features than their tool, like a lot more different kinds of operators, and there's a few differences in what kinds of operators there are as well. But basically, it's the same core ideas, where we have these operators here, and they basically form like an imperative programming language that will again basically just drive OpenGL in a very basic 3D engine, and then that gets compiled down to a bytecode, and then that bytecode is either in the tool or in the intro. Then there's a little JIT that compiles that bytecode to x86. And then that's what's actually being executed every frame to show these visuals. So if we look at this graph in particular, we can see, so again, these are just operators that are in a grid. Each one of these little blocks is called an operator. And then of course we have positions where there's nothing. You'll notice that this one has this this red square around it, and that means that this is what's called the master position. So when execution starts, it starts here. You can basically think of that as the entry point. If I double click here, for example, the entry point is just this empty cell over here. And then of course we get nothing on the screen. I can also double click like one of these, for example, and then we get a bunch of GL errors in the console, but the thing did actually compile. But if we go here, for example, then we're back to normal. I think if we go like here, for example, we actually get some compile errors. And in our terminal, we should even see like there's a compile error and there was an argument that was not provided, which is called aspect greater. Which is this guy, or that, yeah, that's calling. Oh yeah, no, it's there's a subroutine called aspect greater, which has an argument, which is called ideal aspect, and then we didn't provide that argument because we're down here in this, and we need to make a local variable that has that. I'll get to some of those details in a minute as we kind of dig into this, but so execution will start here, and then it basically moves down these operators and executes them one after the other. Also, by the way, this blue rectangle here represents where my cursor position is. So for example, if I click somewhere that moves my cursor, I can also move the mouse around. You'll also notice that each of these operators, like if you think of the data model, it's basically a like set or a map from positions on a grid to operators. And then the operators have like different like types associated with them. For example, the clear operator has a bunch of, so like we have, sorry if I'm not explaining this very well, but I gotta figure out how to describe it. So each position on this could like we don't store this in a grid. We store this as a map of positions, so that only the positions we actually use are in the data structure. So it's just a hash map from position to operator, and then operator is basically tagged enum that has a bunch of different kinds of operators. So for example, there's a clear operator, there's a local operator, there's a call operator, there's an if operator, all those kind of things. Because I think that's actually called a conditional operator, but we write if here. Studio C, how's it going? And then each of those operators has one or more of what's called expressions. Now, expressions are in the data model just strings, but then depending on which kind of operator it is, they can be determined in different ways. So for example, this clear operator here has 4 different expressions: red, green, blue, and alpha. If we get rid of everything else that happens, it should basically just clear the screen, and we can put like 1 here, and then we get green here. Doc Retroid, thanks for the follow. So yeah, so that's kind of how that works. And these, of course, are interpreted as basically values that will change at runtime, which end up being doubles. And there's, a whole variable system there. So for example, I can say hi, and then you'll notice this goes red because this didn't compile now. And it should give us an error, undefined variable hi, because we could actually make a variable there. But yeah, this is basically just clearing the screen. So that's kind of the idea. Generally, control flow just goes down like from one operator to its like child operators or the operators beneath it. And then there are some of these that break that flow, but very few of them. For example, this is CL, stands for call, and that will call a subroutine. And so you can see these other SB operators here that actually define subroutines. Trilater says execution stops when hitting an empty cell. Yes, that's exactly right. So it will go down until it actually hits something here. So for example, I think this won't actually work because we can't put a subroutine under something else. And so that actually breaks there. But for example, like, yeah, I mean, you can see like here, there's a lot of these. But yeah, it'll just go until it hits something empty. And then, yeah, so calls will be subroutine calls. So within the context of this stack, it will go over here and then execute this and then return. Same with this one, executes this and then returns. And then down here, it will call this one, I think. Yeah, render pipeline. And then, yeah, that will basically do the same thing for all these scopes. One of the things that we're going to do soon also is have operators have a width. So I could like click on the right side of this and drag it out, because one of the things that's kind of annoying is that the only way to like go into a different stack is to make a subroutine and then call that. And that's kind of tedious. But it wasn't something we had to do before last October. So that's why it's not in here. And the reason why you would want to do that is, first of all, for organization. You want to have like a lot of these smaller stacks rather than like one huge stack. But more importantly, some of these operators actually have operations that are scoped. So for example, these LC, they make local variables, right? And so anything beneath this within this same stack can refer to this original width variable here, and it will have this value for that scope. Same with original height. We also have the ideal aspect, which is what we want our aspect here to be. And then we change these variables called width and height, which I can get to some of those built-in ones later. But generally, this will push, like, it'll find a variable called original width. It will push its current value if it has one on the stack, then set it to this, and then it will execute all of the stuff beneath it in the stack. And then on its way back, then after that, it will sort of pop all these off. So these are scoped, and generally, like if you want to have two different routines, for example, down here there's a big rendering pipeline, and we have all these different stacks here that represent different passes in the pipeline, and different passes will want to like bind render targets and those kind of things, and you only want that scoped binding to last till the end of this stack and then go back. So we need a way to make like different scopes like that. And currently the only way to do that is to do subroutines, which was more of a way to reuse code actually. But we ended up also using it just to create different stacks, just because we don't have any other mechanism for that right now. But eventually, of course, if we are able to like click and drag and have these have width, then we can just execute each stack underneath a given operator to make scopes that way. And any operator would be able to do that. Dark Second, why did you go with a visual language instead of a text-based one? So there was a few different reasons why we wanted to have a language like this. I don't remember all of the reasons off the top of my head, so I might have to think for a minute. But that was definitely something that I thought a lot about. And I think that the reason why was because with a textual language, I would have had to spend a lot more time on things like parsing and syntax and figuring out how those things would work. And I think a visual language was just a lot easier to make, to design as a language, if that makes sense. So that was one major reason. Another one, I think, was that we had a couple guys that wanted to use this that aren't programmers, and it's unfortunate that the language ended up being as low level as it is, because they still kind of can't use it, I think. But it was always designed to have that kind of possibility that you could teach this to someone who wasn't used to using text-based languages. Although I'm not really sure if that was a goal that was really achieved, which doesn't really matter that much at this point, because there aren't that many of us in our group. So, I mean, it works for me, which is kind of the most important thing. Then the other guys and I can collaborate, and it's just that I'm the one sitting in front of the keyboard. So that ends up working out. But I think that was kind of the reason, is we wanted to have something that you didn't have to be a coder to use. And also that we didn't have to spend time on syntax. Trilater, when calling a subroutine, does it have access to the local variables of its caller? So there's a little bit of a detail here. So we have something called arguments, and arguments are... So the answer is yes, by the way. I should just say. The answer is anything that you would have had in the parent scope, you have in your own scope. But we have these things called arguments. And if you go, like, if you have a subroutine, you can have as many 0 or more argument operators beneath that. And an argument just has the name of a variable that this subroutine expects to be there. So for example, this one needs the ideal aspect. If we go down, so the ideal aspect is defined in this global. If we make our entry point this operator, you'll notice that this call has an error. And it's calling this subroutine, and it's because this argument was not satisfied, because we started executing down here where this wasn't part of the actual scope, because that never got executed. if that makes sense. So the answer is yes, and then we also have this argument mechanism which allows us to actually have like compile time errors if we make an incorrect graph. Yeah, it is a lot like something like Scratch or LabVIEW or MaxMSP or Pure Data. Absolutely. It's a lot like all those things. Vern Bones Vag. It works for me, which is the most important piece, Ferris 2017. Yeah, but it's true. Like we're a demo group. We're not like trying to make money off of this stuff. We want to just make tools to make our life easier and make it more fun for us to make demos, which is what we want to make. So it is kind of the most important thing that it's usable by us, and anything else doesn't really matter. So it is just the way it is. So that's local variables. We also have global variables, and that will overwrite the value but not push it to a stack and then restore it later. So it's kind of like the value escapes the scope, and that's useful for a couple cases. But of course, that's one of the things you kind of have to be careful with. And this argument system doesn't actually work with globals. You just have to assume that globals are available, because it's really hard to check, because a global could be set at any time, or it could not have been set that frame. So there's some issues with that and the state being persisted that you don't want to rely on those. But they're useful for overriding certain things. Like in this case, they're basically used to set the width and height. So another thing I should say before diving into too many of those details is that there are, like, that kind of explains the control flow and the fact that we have variables. We also have some like conditionals and stuff. But because we have variables, we use that mechanism to also pass in variables from like the tool itself. So for example, when execution starts, there's like a big list of variables, and some of the ones that are guaranteed to be there are like width, height, and time. And I think those are the only ones that we have, but I could be wrong about that. I don't remember. Width is the width of the viewport in pixels. In this case, it's actually this entire width here. And then height is the height of the viewport in pixels, which is the entire height here. And then this first bit of code that you see right here, what it's actually doing is it's saying, okay, we'll take the original width and make that equal to width. We'll take the original height and make that equal to height. We'll calculate the ideal aspect, which is the aspect ratio that we actually want for a viewport. And then we basically override width and height with these guys here. And then set the new viewport to be that new width and height that we wanted within the original width and height. And then we're going to call the render pipeline, which is all this stuff, if that makes sense, right? So that's kind of what this initial piece of code is doing, just to kind of set the stage for what this looks like, I guess. Ep.002, I missed the start, but I assume you said what this is programmed in. Yes, so basically everything except the very top level visual layer is Rust, and then this visual layer is C++ and Qt, which is pretty nice. Qt, by the way, is Qt. It's supposed to be pronounced cute, I understand. So sorry if that wasn't clear. Just realized what Vern Bones Vag, that's a hard thing to say. I'll say VBV. Just realized that's why you said cute earlier, I think. And then, of course, so for working with this, basically we have also this. I call this the inspector. So when you select a node, you have all of its expressions available down here. And right now there's just text editors for them, but of course we're going to make a little bit more advanced editors later. And in fact, in particular, one of the things I really want is the ability to scrub values. So for example, if I have this viewport thing and I have, I still want these to be text-based, so I want to be able to interact with them that way, but I might have to like double click to start editing the text. But I want it to be able to like have click and drag to edit the values, numeric values at least. And that should be pretty useful for a lot of things, especially like when we have different values, like a vignette strength, for example, would be awesome to click and drag. But for now, I just have to like go here and edit this value here, which is not too bad because I can just do that really quick. And that's not a problem. The reason why, by the way, that this flashes is because as soon as it sees stuff it doesn't recognize, it just can't compile. So that's why it's flashing, is because it's actually recompiling extremely fast. Like every time I hit a key press, it recompiles. But then if it didn't get a good compile result, it turns black. And There's a couple reasons for that, because I could also just show like the last good frame, but I choose to show the black one, even though it's kind of annoying that it's kind of flickery like this. But I choose to do that to make sure that I know that there is an error. Although I'll probably go with showing the last good frame and then putting like a red line around it or something eventually. Thanks, 0.02. Trailer, what are you using for C++ and Rust interaction? FFI? Yes. FFI. So the in terms of like how the architecture is split up, I can get to this a bit more in a bit, but basically all the Rust code is packaged up in a static library that then the C++ code on top consumes. So like the top level code, the C++ is kind of the driver, and then we have like an editor context with all the tools that it actually needs to recompile and everything and do the JIT and all that stuff that's done in Rust. And this makes things really simple, because like driving Qt from Rust is like, there's some efforts to do that, but at least when this started, those weren't around. And I thought that would be a lot harder to make work nicely than just wrapping all the like core data model bits nicely in a C API and then driving that from C++, which ended up being a good idea, because we have like a lot of different little layers to this application, but they're all really simple layers. So John Hunter 9, will this be open source? Yes, eventually, but it'll be a few months. I want to open source some of this stuff after revision. Like, what I want to start doing is have like a public mirror of the repos that we're working on internally. And then what I want to do is I want to work on demo stuff like privately, or at least like on the stream or something, but then like not have the source that we have, like not have the tip public. But then whenever we release a demo, then I want to update the public mirror. So that's what I'm thinking. And I will dig into the code today just to show you guys how a lot of this works. But yeah, so after showing that, you can kind of see generally how this works. You'll notice a lot of these are color-coded as well, and those are generally meaningful, but it may not be that consistent in the current incarnation. And there's a lot of, like, these operators will change a lot in the next couple of months as well. But basically, the blue ones here are things that change state, and those will basically change, like, GL state or draw something. So, for example, clear will clear the screen. VP sets the viewport. Clear, yeah, I already said that. Quad, I think, is the only one that this uses, just because it's a bunch of full screen quad passes, and then it's ray marching to draw the actual content. But we have other ones, other primitives like cube and stuff. We don't actually have a proper mesh system right now. We may for revision. I don't want to say if we will or not. But yeah, so there's basic primitives here. And yeah, so that's the blue ones. These sort of yellowy, orange, brown ones. It was supposed to be yellow, but I couldn't get bright yellow to look very good in this tool, so I just made them like this ugly orange. And that's these are basically variables, so it's basically only the local operators, and then the global variable operators are the only ones that use that color, I think. Green is all about subroutines. So SB is to make a subroutine, CL is to call a subroutine, and then AR, which you'll see a lot down here, is to define an argument that the subroutine requires. Then purple is flow control. So for example, if is like a conditional. So it will only, it'll basically evaluate this expression as a floating point number. And if that floating point number is greater than 0, then it will execute the stuff below it in the stack. Otherwise it won't. So that's what that is. We use that to like switch parts, which you can't actually see in this one because it only has this one part in this project, but that's kind of the idea there. Then we also have like repeat. So this will evaluate this expression once, and then as a floating point number, and then it will decrement that by 1. It'll run the stuff below it and then decrement that number. And as soon as that is less than or equal to 0, then it will stop and exit that scope. You also see pink over here, which has to do with render targets. Because there's a lot of things that have to do with render targets specifically. So RT will define a render target, and it'll have like its dimensions, depth buffer, and different formats of its color buffers. It can have one or more of those. There's also binding render targets, which is when you're going to draw to them. And then we have this red stuff, which is all about shaders. So we make a GPU program, and this program node will actually bind this vertex shader and this fragment shader, for example. And then these ones that start with U are different ways of passing uniforms. So for example, URTT is uniform from a render target texture. We could say whether or not we're using like, yeah, color buffers and stuff. And then these UFs are just like floating point uniforms. You can also see that in some of these expressions, and sorry if the font is a little small, I can't really resize that, but you can see in these floating point expressions, like this is the name black, so it's setting a uniform, which is how you pass variables to shaders. Setting a uniform called black with a value. You can see it looks like it calls a function called sync, and then we get post : black. And what that actually means is that it will grab a value from the sync tracker. In this case, under posts, if I can expand this thing's a little touchy here. But then, so this was post black, and then you'll see somewhere in here, there should be a black thing here. So for example, I make that 0.5. This is fading the screen to black. That's what the idea there is. Sakes, just random question that popped in my head. How long does it take for your team to produce a new demo with these tools? So we did 3 demos with this tool now. We did Almost Infinite last summer, and this was a very different version of this tool. And that did not take very long, although it took me a long time to do the initial post-process pipeline, which we're still using bits of now. So that was a week or so, most of which was still spent on making the tool work. Elysian last October, spent a few months on this tool, and then the demo took about a week, maybe 2 weeks, I think, actually, from when it initially started. And of course we had the music before then, but we really worked, like most of the visuals were done in that last week for sure. And then that migraine one we did in about 5 hours, and then we hadn't changed the tool at all from Elysian, and just made that. And it's basically the same project as this, but with different shaders and different sync tracks. And that was about 5 hours, which is pretty cool. So we're getting pretty effective with it, and we're getting to the point where we're changing it a lot less. But of course, there are some things that we need for April. But I think that like the core ideas won't change anymore. Like this programming language here, or I should say this operator system, really. I think of it as a programming language, but I should say the operator system. That won't change, even though like which operators we use will definitely change. And the way we do sync won't change fundamentally for a while, at least. I know I want to have some different kind of curves, whereas these ones end up being pretty basic, and I can probably show some of that later. Yeah, that kind of stuff. Basically, I wanna go over this tool this week, and then I think next week I want to do kind of a deep dive into Elysian to kind of show you guys how that worked within the context of the tooling, and then it'll probably help to better understand how some of this works as well. But I feel like that'll take over an hour to do on its own, so I didn't want to do that today. I wanted to talk about some more lower level details of the tool, I think. But then, so just kind of following in this project, and a lot of our projects are kind of done this way, where we have this entry point that basically figures out like the aspect and sets up our frame here. Then it calls this render pipeline, and render pipeline literally just calls a bunch of other subroutines for different kinds of passes. And the passes that are here are really specific to the different kinds of like rendering things that we have. I can kind of show each of them one by one, but like I can kind of, yeah, sorry, forgot how to talk for a second. I'll probably just show each of these, just kind of how they work, because it is kind of cool, and I really like the post pipeline that we have right now. It's basically the same that we had in Elysian, but with a little better depth of field, and that's about it, I think. Considering how thin the UI layer is, why use Qt instead of manual drawing? Mainly for speed, and the fact that I don't want to build a UI system, which I would have to do with GL. I also don't want to use something like ImGUI because it didn't have... mainly because I didn't want to learn something new, and I knew that this would be fast. I still don't think that ImGUI scales that well, even though it's really fast to like build UI systems. But yeah, there were a lot of factors, but mainly it was because I knew Qt, and I knew it had everything I needed, and I knew it would always be fast. The only custom control that we really have is this operator editor, and that ended up being not that difficult to make. Yeah. So in this rendering pipeline, And I mean, the rendering pipeline is a bit sort of orthogonal to the tool because it's kind of like what we made in the tool, but it also kind of shows like I can express kind of how the tool is designed through using that as an example, I think. And I think that's valuable because a lot of the way that these operator graph, like what kind of operators we have in this graph and how they work is really like driven by the content that we wanted to make. And also the problems that I had beforehand before making this system really drove like what kind of operators we have. So the first subroutine this calls is init render targets, and that is this one right here. This big stack, excuse me. And all of this is just a ton of these render target operators. And they basically what a render target operator does, it gives a name to a render target, and these have to be unique. So I think like if I copy the name from one of these and then put it in here, we have problems. I can undo that. And then they have their width and the height of the render target. And then we have whether or not it has a depth buffer. I think this one needs it, maybe not. And then we have the formats of its color buffer. So you basically always need a format for one of the color buffers, but if you specify multiple formats, like in a comma separated list, you will get multiple color targets. So that's how we get, basically one or more targets, and then we have to specify the format for each of those, which is generally what you want because that way we're able to specify. Like I had it before where we had a number of render targets and then the format of all of them, but then they all had to be the same format, and that's often not what we want, especially when building a rendering pipeline like this, because like especially our depth of field will render to multiple buffers with different formats, so we need to be able to do that. Ep.002, did you consider using F#? I know you're a fan and made cool stuff in F# before. Is Rust a better F# for you now? So actually the very first, even for 64K, I did start doing tooling in F# summer of 2015. Just kind of give you guys a timeline. This version of the tool with the operators and everything really started around July, right after Almost Infinite and then For Elysian. But the whole Qt and Rust thing started last March, and before that it was F#. So, like I did consider F#, but in the reason I didn't use that was because for the UI, like I didn't have a lot of options. There's basically WinForms, which is supposed to work on mono, but I found it extremely unstable on the Mac. So, and I needed something cross-platform. When I did the F# tooling, like I was able to move really fast and I was able to make some cool stuff, but I didn't really know what the tooling would look like. And then that was kind of a huge setback that was not as cross-platform as I wanted. So I basically ditched it for that reason. Qt was a lot easier to set up for that. And then later, of course, a lot of the groundwork for our more recent tooling was redone in Rust. So it kind of made sense to do something that would work with that rather than like use .NET or something. I built most of this on Mac, but it was designed to be able to work on Mac and Windows. But yeah, so that was a big deciding factor, and that was another reason why we used Qt. There is the added benefit that there's like a shared code base that's exposed by a C API, but of course, like in .NET, we could have had the same thing with pinvoke. So that wasn't a huge factor, but it was mainly the UI thing. Yeah, and Rust, I'm generally pretty productive in it at this point. But yeah, so we init all these render targets, and I don't really want to go over what each of these are because they're basically like for different passes. But so when talking about like the context in which these operators actually execute, it is actually a little bit mixed because so the idea is that this whole thing gets compiled to a function that's called every frame that actually does all your drawing. That's kind of the idea. But then there are some of these operators, for example, the render targets, but also the shaders. And those operators will need to like, for example, if I change the height or the width of one of these render targets, it basically needs to be recreated. So there's like a separate asset management part of it. So the code that runs here has a context, and that context has basically storage for all the variables, and some stacks for maintaining GL state for like pushing and popping onto, pushing onto, popping off of. But then it also has an asset manager, and the asset manager will handle storing and updating render targets. That's also why we have to give these names, but also to refer to them when we actually bind them. But it also will do file watching for different assets. So we don't actually have like textures on disk. We don't have image support in here anymore because it's for 64Ks. Could probably add it back to the tool, but then there would be some like conditional stuff, and I don't want to deal with that. But shaders, like in the tool, we have an asset manager that sits there and you specify file names and it will watch those files. And if I change anything in any of those files, then the shaders will be reloaded on the next frame before this function is called. So we always have the latest shader available. And then of course, if it fails to compile, it won't actually replace the shader. So we just run with the last one. But yeah, so there's like that difference in sort of asset management in the intro and then in the tool. But the bytecode itself doesn't really care about that because all these just get turned into indexes anyway, into a big ordered list. But yeah, so we need to have some parts of these like execute sort of as part of that asset manager just to make sure we have the actual data that they need ready here. But these render target ones actually have to be like executed because, like I said, if we update the width or the height or something, for example, when I resize this, that ends up changing what the value of the width and the height variables here are going to be. So it ends up recreating all these render targets. Yeah, and then, yeah, so I can show the shader reload actually. For example, I think this is just a lot of the shaders that we have. They're in the assets folder of the editor right now, which kind of sucks, but we just deal with it. So I think this is some shader that I'm using called GI the fuck for reasons. For example, let's find something to change. I could change the background here to this tunnel thing. For example, if I save that, then this just updates. And now we have this tunnel thing that this is in. And that's kind of fun. So that's kind of the idea, is that sit there and change the CPU code in here, and then go and change the GPU code in the text editor, and it all just kind of works. So that's the idea. Sorry if the stream has worked. I'm not seeing anything on my end. So don't have much to say about that, unfortunately. But yeah, so basically we call this subroutine in order for it to like refresh all of the widths and heights for all the render targets. And then we go through all the different passes. So for example, the first one is a gbuffer pass, and that will basically use ray marching to fill in some gbuffers. The gbuffers themselves, I think in this case we have, I believe it's like world position and something else. Let me actually see. It should actually say in the shader, I think. Yeah, okay, we have the view position and then the color. That's what we have here. John Hunter, yeah, it's a trend. I name things like that when I'm just throwing together things. I wonder if I should actually be able to show the output of these. But why don't I just enumerate the passes? So we have a gbuffer pass where we just use ray marching to dump the color of each pixel and also the view space position of each pixel. Then we have a depth of field pass, which will basically do depth of field on that. So there's a lot of details with that. This whole bit right here is the depth of field. Then there's a bloom pass, which will give us this kind of glowy look. There's a compositing pass, which puts all the output from the bloom and the depth of field together. And I believe, okay, no, that's all it does. Just composites those. We then have a masking pass. And this will, like in Elysian, if you saw like the mirroring and stuff that we did, in fact, I should be able to show some of that, like logo fade, for example. Yeah, puts all these logos on here. Should be able to have some of those mirror masks that we had in Elysian as well that I can enable and disable. That's all done in that pass. We just kept it around because it's kind of fun to play with. Then there's a chromatic aberration pass, which will do some really fun stuff. Yeah, so this basically gives us like RGB separation, and we can really crank that thing. That one's pretty resilient. So that's pretty cool. And then We have a tone mapping pass, which will do things like vignette. We have an exposure that's applied there. Also, there's some additional mirroring done at that pass. And then after that, we have FXAA in this case, which will do some anti-aliasing as a post-process at the very end of all that. FPGA Nugget was cross-platform tools important because of multiple people on projects? It was initially. It ended up being more important because at the time when I made a lot of this, I was most of the time using a Mac. Just when I was like going around, I was traveling with a lot with a Mac. Had to be able to work on it there, and then our target platform ends up being Windows. So we needed it to also run there in case we had to debug stuff, rather than just trying to build the intro, rather than saving on the Mac and then building the intro on Windows back and forth. So it's better to just have a tool that actually supported those platforms. We don't support Linux because none of us are using Linux. I mean, we could, but we just don't. And interestingly, the cross-platform thing never really, I think, had any real issues except for the JIT. And I'll probably go a little bit over why in a bit. Basically, because there are some small differences in the ABIs of the two platforms, and there's some stack alignment stuff that we ran into that's Mac specific. So that's the idea there. And then, so I want to see if I can just show. So what I'm just going to do is I'm just going to use these different buffers as inputs to the very last pass, and that should allow us to show different ones of these. So for example, here, that should have been the G buffer target, but it's probably not showing anything because it's the view position. So that's probably not that exciting. John Hunter 9, how dare you dump Linux? We're just not using it, man. Dark Second, how do you do textures, pure GPU, or do you have operators for it? So in Elysian, and also in this one, like this texture, for example, that's just pure GPU. So that's just what we're doing. I mean, so here, the thing about that is, like, I thought a lot about having to do like meshes or textures or whatever in these kind of operator graphs. And the way I think that I would handle that is that I would have different kinds of the same kind of graphs so that we can reuse the same editor, but have it edit different things. So there would be like a different operator graph for textures or a different operator graph for meshes, where they would basically describe the same thing, but their execution context would be a little bit different, and the set of operators that you get to use would be a little bit different. But I haven't actually gone into implementing any of those, so we end up just doing textures on the GPU for now, which is not too bad because it's still pretty fast. Daniel Collins, same for our Amiga stuff we did in 2014, supports Mac and Windows. Yeah, I mean, it's all about, like, these are really free time projects, and like supporting another platform just to support it would be a really bad idea because it would just take a lot of time that could better be spent actually working on content. So that's kind of the idea there. But then, so then this operator graph specifically is really specialized for like driving a very simple OpenGL based 3D engine, if that makes sense. And it's pretty low level. So let's see if I can actually show some more of these. I could probably show some of these depth of field targets at least. Oh yeah, and I also have the index, so I actually can show this. Been a while since I dug around in here. Index 1 maybe, yeah. So there's our color just from the raw G buffers. It's really noisy, which is kind of to be expected because it's basically just black and white. At least in that one. This is definitely a test. Let me see if I can change that background again. See if we can get some a little bit more interesting things here. Like this is that sort of neon tunnel thing. Pretty noisy. But again, this is before anti-aliasing and before a lot of the other things. So there's our color buffer. And of course, our position buffer wouldn't look very exciting. The depth of field has a few different passes. We have the circle of confusion target, which is what we use to basically figure out per pixel how much things should be blurred. And we have the far pre-multiply target. I don't quite remember what all these buffers are, but this is like for the depth of field, we actually split up our image into like we have like a focal distance, and everything in front of that becomes the near field. Everything behind that becomes the far field, and we process the near and the far field separately. So there are a bunch of different like far field blur targets and stuff as well. So this is going to be the far after it's been blurred. So you can see it gets blurrier as it goes back. So the COC, that red texture that we saw earlier, determines the width of that blur per pixel, which is why like the far away stuff is red. I can show that again really quick. So by the way, like even being able to show buffers like this, I'm doing it in kind of a hacky way, but the fact that I'm able to do that this quickly and just like show the different buffers is extremely valuable. And also every time I'm like changing these targets, it's actually recompiling the graph into bytecode and then recompiling that into x86. So it's really fast. We have also the near field stuff, and we actually do 2 blurs on the far field. So this is even blurrier, a bit smoother, and we get really wide bokeh on that, which is pretty cool. The near field stuff, I think we also do 2 blurs on that, but I can't remember exactly. Oh yeah, we do a downscale first because we take the near field. The near field processing is a bit more expensive than the far field processing. So we want to take that down first, and then we'll blur it at half res. And so the near field blurred looks something like this. So you can see it's blurrier as it gets closer to the camera. And then we composite this together. So if I show you the output of the compositing pass, then we have this. So this is the blurry far field and the blurry near field blended together with the original image. So that's why we have some stuff that's in focus and some stuff that isn't. If I go into the depth of field, for example, we can adjust some of those parameters like the focal depth. Right now it's at -20, it looks like. For example, we could say like -5. Be a little closer to the camera. For example, you could say like 0 to -20. We can like interpolate that. See, it moves there. All that cool stuff. I'll comment, do you package the final exe from the editor? Seen some fun chain with NASM and all package player recode and do the exe, or do you use some side scripts? So I have file export project. I can show you what that'll give us. So I'll just put this on my desktop, for example. And then I'll open it up in a thing. So what that does is it dumps the bytecode and some assets, like basically a binary blob that is serialized. And then what we do is we have another project, it's just a Rust project that actually uses that as an asset. And then we just build that project. So we don't dump to exe directly, but we do basically we do everything else here. And that's also because there are a couple additional things that we want to do with the code. Specifically later. Anyway, I can kind of show you what that dump looks like. It's kind of cool. Let me open this. So that dump file that just made was about 63 kilobytes. And this is what it looks like. Let me see if I can zoom in here. I don't think I can, though. But it basically has a bunch of metadata about like the render targets, and also the bytecode for the operator graph is here. And then later it has, of course, all the shaders just in plain text. We don't even minify these, so there's a lot of like white space and stuff in them. And that really doesn't make a difference in our case. I mean, it could probably get smaller if we minified these, but it hasn't been an issue, so we haven't done it. A lot of shaders. And at the end, we have another string table out here, which is basically used for uniform names. And I think that's about it in terms of what's here. There's also, of course, the data from the sync editor is also included in this in a serialized format. So a lot of the stuff up here is that. I'm not really sure what the order of the actual data is, but I mean, it's all binary here anyway, so you're not really going to see it. But of course, the textual stuff is all at the end to sort of pack that together. But yeah, so this binary blob there's an include bytes macro in Rust that will just include some file as a slice. And then that ends up being deserialized in the intro and then run. Like the bytecode part gets JITted. The asset manager in the intro will go through and look at like all of the render targets it needs to make and all of the shaders it needs to make, and pulls all the string data from the blob and actually compiles the shaders beforehand. We also have something called preload points, which is part of the executable, not part of this data structure, where we will take a bunch of like time offsets in the demo and just run those onto an off-screen buffer, and that's to sort of warm up the GPU with our specific effects, because there's a lot of things, there's a lot of optimizations on the GPU that are going to happen at the very last moment. Like a lot of things are going to be baked into sampler units and all those kind of things. So we want to give the GPU an opportunity to do that up front rather than while the demo's playing, and that will reduce pauses when we switch scenes, for example. Because that'll basically all get baked the first time you actually draw something with certain shaders, for example. So that's why we do that. Anyway, that's basically the export process. Is we export that binary blob and then we rebuild this executable. The reason I'm not showing the rebuild is because I actually tried it earlier today, and it looks like the some of the no STD stuff, maybe not that, but like some of the lower level stuff in Rust has changed a bit again, which, I mean, we use nightly, so we kind of expect that. But yeah, I couldn't build that earlier today, and I didn't really try very hard. I didn't like try to fix it. I just ran it as was, and it wasn't working anymore. So just decided not to show that today. Flitch 13 sounds like the control Vulkan gives you would be pretty useful there. Yes and no. I mean, it would be more code to do the same stuff, and maybe we could get it a tiny bit faster, but that's not really where our bottleneck is, because we're doing most of the stuff in shaders anyway. You know, calling the Vulkan API is way more verbose though, and it will make the exe a bit bigger. Yeah, that's basically it. Also, we don't have Vulkan on Mac. There are emulation layers that are commercial that I've seen that will basically bridge the gap between that and Metal. But yeah, don't really have that here now. So we just use GL. We use GL 4.1, I believe. And again, that was because of Mac, because that's the latest version that Mac actually supports. But that's fine. I'll comment down calling a bit, probably a lot. Yeah, I actually think it would make at least the code that we use a lot bigger, but I don't think it would be that significant in the 64K though, in terms of like executable size, but I do think that it would definitely be significant in terms of workload for not very much benefit. At least not with what we're doing now. If we were doing a lot more stuff with like dynamic buffers, especially like mesh generation, and like moving data to and from the GPU a lot, I think that would make a bigger difference. But because we're basically load everything up front and then just like switch shaders, I don't think it really makes much of a difference. So yeah, Colin. Also, if you use shaders, if you almost use shaders, then there isn't that much of a win with Vulkan anyway. Yeah, that's kind of what I'm thinking. Plus, I know GL, so don't think I'd have that terrible of a time picking up Vulkan, but it would definitely be a significant time sink to switch everything. So yeah, in this case, it's quads and pixel shaders. In Elysium, we did, of course, some meshes, but the meshes were static. And then it really didn't matter. Just use some vertex arrays, and we're fine. What other passes are fun here? Well, everything else is really just a post pass after this masking target, for example, or after the compositing. So it isn't really that exciting after that. Although you'll notice that this doesn't have anti-aliasing now, because we have to output some luminance. Also, there was actually a bit more here, and I think that's actually because the tone mapping pass is where that came from. So for example, if I put the composite target in here, yeah, the main difference there is the compositing and the tone mapping. And actually, I think that actually is getting run through FXAA, because I think this last program here, yeah, is the actual FXAA. So that actually probably was anti-alias. It was just too noisy anyway, because there is a threshold there. This scene is crap, by the way, but it's just something that's fairly useful for testing, and something I really don't mind showing right now, rather than some of the other stuff we're working on. But that's kind of like all there is here for what we're using. Of course, there's a lot of details in the actual shaders and the passes themselves, and it's a lot of which I don't think is that, like, it'd be interesting on its own, but it's not that interesting in the context of the tool. And it's something that would take me a really long time to go over if I wanted to go over in any kind of detail. So I probably won't do that right now, except maybe when we go over Elysian, I might dig into some of that because of, kind of why we have things set up the way we do. And there's kind of an interesting lighting trick stuff that we use. So I think that'll be a lot more interesting. Whereas here, it's just like we dump the view position and the color to a buffer, and then everything else is just kind of external. Do have some kind of fun things here to adjust the scene. But yeah, then I think I want to talk next about, or actually want to show some of this stuff. But I think I want to, what is this? I have different kinds of shapes. Slashes. It's kind of cool. But yeah, talk about kind of the lower level details and how the different bits of the software itself fit together. Base effect, how long did it took to code the demo tool? So there were a few different incarnations. Like this code base started last March of 2016. And then I don't think I've touched this at all since mid-November when we did migraine. So that's like, I don't know, bad at math in my head right now, 8 months. But that last month wasn't really a lot happening. So about 7 months. Seven months sounds pretty accurate to me, because at least working with like 64K tooling, the synth was already done since then. We hadn't really touched it for that demo. But yeah, that includes like the previous incarnation of this tool and this one. It's the same code base, but like I said, the scene graph, the way we do the actual rendering code, is a bit different now. This code in particular started in mid-July with this operator graph. I also spent like a few weeks during that time playing with executable packing. And then, of course, the last couple weeks before mid-October were actually spent using the tool, but also changing the tool while using it. So there was kind of that work, but 8 months is about right. And I'm generally really happy with it, actually, like, which is not something I've been able to say about a lot of tools I made before, but it just has the right stuff. Like, and it's pretty robust. Like, I can just sit here and mess around with this graph and click around, and that's pretty cool. Hit a bunch of keys to create a bunch of new operators. Right? And it's really cool when you have a tool that's this solid. This is kind of my big test, is if I can do that kind of stuff, move around big chunks. And then if I can just hold Control Z and everything actually works, then it's a pretty good tool. Like, that's my big stability test. Oh, I love doing this. And eventually we'll get to the beginning of the episode. Cool, and that works again. Of course, we can redo all that, but yeah. So, I mean, it's generally like solid. I'm really happy with the architecture. So like when we're adding nodes and stuff, we have to touch a lot of layers, but it's not actually that bad. I'm generally happy with how the different pieces of code fit together. There aren't that many hacks. There are a couple hacks, like the fact that the asset like management system doesn't know about like project folders, so all the assets are actually in the editor's assets folder, stuff like that, which really doesn't matter that much when we're sitting here working on stuff, because we can just check out specific versions of the tool, for example, to find all the assets for a specific demo. And like, we're not really opening older projects anyway. So there's those kind of things. You forgot to save. Oh wait, yeah. Yeah, undo redo is extremely important in a tool like this, because we're just going to be tweaking stuff all the time. So that really matters. And yeah, also that's one thing I didn't go over, is to create ops. There's basically a ton of buttons on the keyboard that will create different kinds of operators. There's a lot of the keyboard that is used up for that. And it may seem kind of random, like what goes to what. But it is actually like a pretty decent system, although there are so many. I can, of course, undo all that. It's pretty fun. But yeah, so that's generally how it works and the kind of stuff that we do in the tool. But then, of course, there's all the lower level stuff, like how all the different pieces fit together. So I kind of want to talk a bit about that because there's some really interesting stuff in there. So I'll go over to my Blackboard view. How fancy am I today? Oh, I can't move that window. Not that fancy, apparently. There we go. So, like, how do I want to explain this stuff? Let me adjust a bit. So basically, we have this. How do I want to explain this? Because there's a few different parts, and we have names for the different pieces. So, for example, one of the things that's sort of at the center of this is something called opus. My great mouse handwriting. So opus is all about operators, which is where the name kind of comes from. The names in here are a bit goofy, but that's just because I have fun making names. Hardcore Head 87. I understand like 10% what's going on, but it's fascinating to watch. Cool. 6, yay, back to school. I would have loved to learn this stuff in school. So opus basically has to do with the actual operator graphs. So actually making little operators and yeah. So it has to do with the actual operator graphs. It has to do with the actual bytecode, which I guess I can... Oh, it looks like code. It also has to do with like project management. So for example, all of this is in XML. Like just an XML project format, which is literally just a serialization of the operator graph you saw earlier. I'll come up with a good teacher this time. Thanks, man. And so Opus has to do with all of that. It covers like project management. It covers the actual operator model. It has the compiler to go between those. And it has the bytecode. And yeah, and so there's actually 2 parts to Opus. Let me adjust here a little bit. Make this a little bit smaller. How's that? Yeah, that's a bit better. There's actually 2 parts to that. So we have, do this. There's Opus, and then there's the Opus runtime. Yeah, Colin, I slept at school and spent the night coding Amiga. That was very similar to my school experience. So the Opus runtime itself has, this is the thing that will actually like handle the bytecode, and it also has the basic 3D engine in it. And the 3D engine is really basic. It mainly is just built of abstractions for stuff like making vertex buffers or shader objects and those kind of things. Super basic. And it also has a constraint that it can't use the standard library. And that's because this code is actually shared between the tool and the intro. So if I'm going to add another barrier here. And we're going to say everything on the right of this is like stuff that can be in the intro. And everything to the left of this is stuff that can be in the tool. So the runtime, again, has that little like 3D library, and it also has to do with, it has the JIT that will turn the bytecode into x86 and execute it. So I guess I can add a couple boxes here for the JIT. And then we have the engine, ENG. Just super basic GL engine. This relies on a couple other small packages. So we have a bunch of different bindings for like different APIs, for example. There's things to like allocate memory. There's things to have like GL bindings. And again, all these cannot use the standard library in Rust. However, they can use, in some cases, the C standard library because that's exposed through the VC6 DLLs, which are system standard on Windows. But that's more for like the actual runtime. Let me add a couple other components here. We have another one here, some room up here, and I'm going to call this Rivet. Now, Rivet is a small thing made of metal. You know, on jeans where like the pockets meet the pants, and there's like those little circle things that are made of metal. Those are rivets. And so we use those. Rivet is like the project that is the actual intro itself, right? Like this is, if we build this, we get an executable out that is the intro itself. So Rivet, let me find another color for dependencies. I'll use blue or something. So Rivet depends on the Opus runtime. But then we also have some of these more libraries. So for example, there's a Win32 one. There's a GL one. There's an alloc one. And some of these are like interdependent. So for example, the Win32 relies on the alloc one. Rivet relies on basically all these. And there's like another, there's a couple of those other ones. And then like the Opus runtime also relies on like the alloc one. See what I mean? So you can kind of see that there's these very basic things. And these are all basically separate Rust crates, just to keep those separated. And just as small as possible. And then, so again, Opus runtime will deal with like taking the bytecode and running it and also doing some 3D stuff. And then Rivet is our actual intro. So Rivet will basically just make a window. It will deserialize the blob, the data blob, which is, again, something that the Opus runtime knows how to do. And then it will just start running the intro. Now, when we talk about like that binary blob, so that's the kind of thing that ends up being packed up in this kind of stuff. That is serialized from the tool. So like the Opus runtime just knows about bytecode. It doesn't know about operators, right? But it's still part of, the runtime for that. So we kind of still name it that way. But the operators themselves exist at this level where Opus is. And so Opus has, I'll answer this really quick. GL is not RSGL, but directs access with CNFFI. Yes. So we can't use the standard library, which is why we can't use GLRS. So we use that. We just do raw bindings. And it's not that much because we use like, 30 functions or something from GL, which is not that terrible to do by hand. And it's a lot less that we use in Win32 and even less that we use for alloc. Fuborg, what are the constraints for the demo a Windows binary below a certain size? That's exactly what it is. It's a Windows binary that's less than or equal to 64 kilobytes in size. So that's why we can't use the standard library. We can use a lot of the stuff that's in the core library, because a lot of stuff ends up being pretty small. But yeah, we can't use the standard library. We do use some of the C standard library though, as I mentioned, because if you're building with MSVC, you can link against the VC6 DLLs. And those will actually give you a lot of those, a lot of what you need there. But generally, we don't need that many things. I think the only like collection we use is a vector, and we just implement that ourselves, for example. So it's not that bad. But yeah, that's why there's this separation here. It's because like you can basically think of everything on this side as like it can't use a standard library. Different parts of it may also not be cross-platform. There are certain parts that have to be, but there are certain parts that don't. And we also actually don't have the non-standard library constraint on the Mac-specific versions of some of these libraries. So for example, the alloc has some Windows implementations and it has some Mac implementations. And on Mac, we can basically use whatever, but on Windows, we have to not use a standard library. So sakes, even my Hello World binaries are larger than 64K. If they're using OpenGL, they wouldn't have to be. There are not that many calls you actually need to do that kind of stuff with GL. And also, I mean, we jump through a lot of hoops to make that happen, but ends up not being that terrible. But yeah, so the right side of the line is like no STD, basically, for the most part. Again, I blur that line a little bit on OS X when it's convenient, but the interfaces are all the same, and don't assume standard library. So this Opus thing, again, is basically dealing with projects, which are, again, just basically a list of operators at certain positions. And then it has a compiler that will take that and turn it into bytecode. And then the runtime itself will take the bytecode and turn it into x86, and then that will actually be executed against the GL library. So the Opus runtime, you basically give it, I don't even think you have to give it a GL context. I think you just have to have one that's current. So like Rivet will bind one and do some stuff, and then the tool will bind one and do some stuff. But Opus is just one part of the tools, right? So that's just about the operator graph, and that's just the data part. Like it doesn't have anything to do with the UI. So that's all in another thing. So I'm not going to add another barrier here. Base Effect, how do you bind the music? Any fancy stuff to sync with visuals? I'll get back to the sync tracker and sort of why we have that. But generally, the music, again, is, so we have our own synth, and that is done in C++, but it exposes a C API, and then we can consume that C API and just have it play and then give us the time. And based on the time, we have some basic animation stuff that will just sort of change values over time. So given a time value, it'll give you a value. And those feed into variables in the operator graph context, if that makes sense. So whenever you call a sync thing from the operator graph in one of the expressions, it will end up being translated to a certain variable that's expected to be set before that function is called, and then comes from the sync system. In the tool, that music stuff, we don't use the synth in the tool. We use a wave render from the synth in the tool, and that just makes things a bit more convenient, and especially to like seek around in the music. And I can kind of show how that works in a sec. But the idea is that that's kind of a pretty separable problem, actually. I guess I can have a box over here though for the synth though. We'll do wave saber. Right beneath my name too as well. That's kind of fun. We'll do this here. There's the, whoops. Looked over at the other screen. Wave saber. There we go. And then this just relies on this. But it's pretty separable from the rest of this tooling. So in addition to Opus, the tool has a few other features, and it also has like an undo system. It has a way to actually expose these graphs. It has like a concept of selection, a couple other things. So then we have what we call, I want to add another dotted line here. And what I want to do, yeah, we have, let me see how I want to do this. I'm going to put EC here. I'm going to put no STD here. And then over here we have the editor. So EC stands for editor context. And that has Opus in it, and it has, so there's basically one project called the editor context, or I think it's actually called domain model because the names have changed over time. But the idea is that has stuff like selection, so I'll put SEL over here, and like undo redo, and like a history and all that stuff. And all that is kind of wrapped up in this project called the domain model, which also relies on this stuff, if that makes sense. So again, this only has to do with like ops, but it's not the driver. And then this stuff will actually kind of bind that into something that like looks like an application that starts to have logic, like it can load projects, or it can save projects, or it can move operators around. Like it exposes something where you can look at the data model, and then it gives you a way to change that, for example. And all of this stuff is still in Rust, right? So we can kind of think of everything past this line as all in Rust, except for Wavesaber, which is C++, but not terribly important. Here we can tie that off. That's C++ up here. Yeah, can't see that. Whatever. And then the editor itself is all the stuff that's done in C++. So this has basically one project called editor, and then it has a bunch of different like, so between here, this editor context, there's a C API that's about here. Let me use a different color for this. I know that I'm being a bit scatterbrained, but there is a fair bit of stuff here. I'm going to use red here because there's basically a C API here. And it basically exposes everything here. I'll draw that with the dependencies again. This will probably be a slightly different blue, but that's fine. The C API exposes this to the C++ layer. So there's a C API in between here. And then we have the editor context as viewed from C++, which is basically wrappers around the main context here, but then it's wrapped up again in C++ objects. So we have the editor context again over here. And then we have the main sort of editor itself. which will basically expose the API and then use this editor context stuff underneath. So its primary purpose is to show a UI and like get a GL context and all that other stuff. There's a couple other bits here as well, which is like the rocket stuff, which is what we're using for sync, and this binds that way. We also use the base playback library to actually play back the audio in the tool. So there's also some of this stuff. Actually, you know what? That's actually it. That's actually at this level. I'm going to be a little bit jank here, but that's fine. Base is actually at this level, and then this stuff actually binds to that. Kind of making a mess here, but... Foodbork missed the part. What was the input to Rivet? Custom instructions. Yeah, it's that binary blob that like you export from the tool. So it's basically a binary blob that has there's one binary blob that it will use to give to the synth, and then there's another binary blob that has all the visual stuff, which is basically the stuff that the Opus runtime needs to actually draw everything, and some additional metadata for assets, which at that level is basically just shaders and a little bit of information about render targets. But that's all in a serialized blob, and that's what ends up going to Rivet. So Rivet is like a standalone project, and when we build it, one of the input files to building it is that binary blob. And then the editor context is another standalone project. Opus is a standalone project, but it's just a library. Opus runtime is also a standalone, but it's just a library. And the idea here is that all this editor stuff is what we're using when we're actually editing the data model. And then at the very end, when we export, we basically call the compiler here to have it export the bytecode and also package up all the shaders. So the compiler, because it knows about like all the file names from the operators and everything, it will actually go and it'll give us like metadata about all the assets, all the shaders and everything about like all the file names that are in there. And part of the packaging process is then going and reading in all those files as well and packing them as part of the binary blob. If that makes sense. A bit scatterbrained, I know, but there are a lot of pieces here. But they're usually pretty small pieces altogether. And I can kind of show you guys some of the code as well, which will probably help. But yes, the idea again is that Foodbork, cool, good to hear. Yeah, so the editor is what we're actually working with. This is all the stuff that we're touching, and then that's just a GUI layer on top of all this stuff, which is actually editing data. When we're ready to export everything, and also when we make changes, because like everything is recompiled whenever we make a change. Like there's in the tool that it has a compiled version of the project at all times, so whenever you make a change, it will recompile, and that compiled thing is what's actually used to show the stuff in the viewport. Basically the same code that's going to run in the intro. And then, of course, when we package everything up, that same compiled results, I actually think it just recompiles because it can. And then some other metadata is all packaged up in a binary blob, which then we build into Rivet, and then we rename the executable to whatever the intro name is. So that's kind of it at a high level. But then, of course, there are a lot of these smaller pieces that are mostly split up based on like responsibility and constraints, because like everything along this side of this line, for example, can't use the standard library. So we kind of need two different Opus projects, one for all the stuff that's on this side, and then one for all the stuff that like can use the standard library, like the compiler, where we want to have a sort of more comfortable coding environment where the size doesn't matter there. So that's kind of how that makes sense. But of course, we do still use this code that has the more strict environment. We still link to that. Like if we do, I don't actually think, oh yeah, Opus does actually need the runtime. So for example, there's a dependency here between Opus and the Opus runtime in order for it to like know what the opcode bytes are and stuff like that. I'll comment at this point, it's a blessing that Rust comes with Cargo. Yes, very, very much so. Very, very much so, because all these end up being separate projects. And it's a lot easier to manage with Cargo than something else. That's absolutely true. Comment says, but for C++, I bet on QMake and CMake. No CMake here. For the synth, we just still use Visual Studio because that's where it was made initially. And then for this top level editor stuff, we're using QMake. And then we end up using NMake, which is like Visual Studio's command line make kind of thing. And that's just because we use, so there's a few different reasons why we use so the whole project uses the nightly 686 MSVC version of Rust. And there's a few different reasons for that. First of all, the synth can really only be built in 32-bit. So we have to use that. Second of all, basically the only way that you can get the compiler to play nice with the VC6 DLLs, which we need to use to be able to not use the C standard library in a lot of cases. Basically, the only way that that's going to play very nicely is if we use the MSVC target and not the GNU target. But then because we also have a JIT, that's going to lock us to 32-bit. And then, of course, all the cute stuff as well, because it's all going to be linked together in the same binary. All that has to be 32-bit as well. So there's some additional constraints there that are mainly driven by our final output binary, but that ends up not being that difficult, especially with Rust up, since I'm able to switch Rust versions all the time. So that's pretty nice. So there's a lot of like Rivet, for example, only builds on Windows. The Opus runtime builds on Windows and OS X. Although it may actually use the standard library on OS X, which is fine in that case. Opus, of course, is fully cross-platform. And the editor context in the editor ideally should be fully cross-platform, and I think they are, but I haven't actually built it on other platforms because some of the stuff that they rely on, of course, isn't cross-platform. So like, I don't think there's anything platform-specific at that level at all, but you couldn't build it because the dependencies have different constraints. And again, that's all driven by the fact that our target platform is Windows, Win32 in particular. And there's some fun stuff, by the way, like the JIT, for example, is cross-platform. And it's the same JIT for both Win32 and i686 Darwin on Mac. And there's some fun details in there about how that works. Base effect, what are the size figures before packing? About 300 to 400K. A little bit smaller than that. But that would not be unheard of. Especially because a lot of the data, like especially the synth data and then some of the like bytecode data and everything has been designed to compress well rather than actually be small. So the compression does really well on it because that's what it's designed for. And it really, like the uncompressed size really doesn't matter, so it ends up getting about that big. So now I kind of want to talk about what like the bytecode looks like and the compiler for that, because I think that's sort of the more interesting parts of this. Then the rest is just kind of glue to make all that work. But that's really the core of what's happening here. That, and then of course some of the top level stuff for making the editor comfortable, but we've kind of already seen that. Oh, and I was going to talk about a little bit about the sync system again. Move away 00. Yeah, sometimes adding redundancy to data can make it more compressible unintuitively. Yeah, you want to make the data more self-similar rather than smaller. It's just a different metric to optimize for. So let me go back to showing the tool again, because I wanted to talk about a little bit what this sync tracker is doing. So basically the way the sync data works is like, so we have in a lot of cases in the bytecode, there are these like floating point values. So some of these expressions are interpreted as expressions that will be evaluated at runtime. So for example, if I take a local variable, the name is only used compile time, but then the value will be evaluated compile time. And this, for example, just all this one does is reference the variable width. So it will just go and look that up, for example. But like here, it will do a multiplication. Yeah, that kind of stuff. Not that terribly exciting, I think. Except here, like the viewport X and Y, start to have a little bit more interesting expressions. But so these are just like, we use the FPU stack, the x87 stack on Win32 to actually like give us this like stack-based compile target that just handles 80-bit floats. So we use 64-bit doubles to represent the floats in memory when we actually have to store the results to variables. But like basically a lot of operations here are permitted. So we have basic arithmetic operations like add, subtract, multiply, divide. But then we have a couple other ones. In particular, we have ones like, they look like functions like this. So for example, we have sine and cosine, and those ones actually are functions. But for example, this sync function here isn't actually a function at runtime. So this looks like a function because we're basically calling the value at a sync track, right? But what this actually does is it gets compiled to a variable that's set from the sync system. So when I do this, what this will end up being is like just some floating point value from this track in the tracker. So this is add mask flicker amount, which if we go into post, we'll have over here somewhere. Add mask flicker amount, it's right here. So that's just some value, and I can basically put any value here, and then I have basic interpolation options. And this is what that whole rocket thing, if you hear me talking about rocket, is that's basically what this is. It's just this way of doing this kind of editing. And this one, of course, is really barren because this is basically an empty project that's used for testing some of the rendering pipeline and some lighting stuff. But it's not actually used for like actual animation. Next week, when I go over Elysian, we'll see that this actually fills up pretty fast. But that's basically all that is. And then, yeah, there's a system that like in the tool, it will ask the rocket subsystem, which is talking to the sync tracker and kind of synchronizing data. It will ask that to basically calculate the values of the different tracks at a given time and then put those into variables in the context in which the bytecode runs. And that's how that is all pipelined. In the intro itself, we don't use any rocket code because it's all serialized tracks. And then we have another system that basically does the same thing, like go through all the tracks that we know about just in order. And by then all the names are gone. It's just all like an ordered list of tracks. Calculate the value for each track and then just dump it in variables. So it ends up being pretty simple. Daniel Collin, I know this tool. Yeah, I think I mentioned it before I got here, but that's this particular sync tracker is written by Daniel Collin. I'll comma add to effects, lose 8 kilobytes. Been there. Foodwork, how much flexibility do you have in content creation? What are the limitations if you compare it with a game engine tool like Unity 3D? So because we're limited to 64K, so like we can basically do anything that'll still fit within 64K. We're not going to be relying on any external like JPEGs or anything because, of course, those are going to be too big by the time they actually are used at runtime. We could, of course, do like mesh compression or our own image compression, for example. So like we could basically do anything like in terms of the content creation, but it's like we could do anything, but of course it's very limited by size when it's going to be compressed in the output. So maybe that's the right answer. Of course, with this tool, we're limited in anything the tool lets, like we can do anything the tool lets us do. But of course, like since we make it, we only make it for ourselves, we can always change like what operators we have in the operator graph or what kind of bytecode that we have. Movie 00, no JPEGs, only bitmaps, right? If they compress well. Nah, but we, I don't think like image data isn't that particularly useful in our case because we can generate a lot of it. Mesh data would be a lot more useful, or like animation data, but then of course that also needs to be compressed, and yeah. Then I'll call on to make my bitmap small by renaming them to JPEG. Good. Yeah. So this particular version of the bytecode and like different kind of operators is of course very much driven by what we needed in these intros. Alcoma says TextGen is all render targets and full GPU. They're too, right? You don't have dedicated ops for that. We don't really have anything that is a texture generator specifically. We just like add some math where we need textures. Like we just write them as parts of the shader. It's very common to just like fork shaders and just have different like shaders for different materials. And I just hard code the values in there. And that works really well for me because like we have the live reload for the actual shaders themselves. So it's a pretty decent workflow. But yeah, nothing fancy there. We just kind of inline everything. Foodboard, confusing meshes, not too detailed. Yeah, it would depend on what we would do. So like if you compress meshes, you probably wouldn't want very detailed meshes. If you generated meshes, you could probably get pretty detailed meshes, but then Then you have to make a mesh generator and tools for working with that effectively. Like 64K is more limited, I think, by what kind of content creation tools you can and want to make, if that makes sense. Like it's more of an exercise in making tools that allow you to make cool content more than it is making your content small, if that makes sense. Because like most very interesting meshes, for example, you're not going to be able to compress them that well. But if you were to generate something similar, which I mean, you could think of as a kind of data compression, but you would rather use that technique rather than trying to compress something made in another tool. How do you make that nice to work with, and how do you make the things that you kind of want to make? And then of course you can say, oh, that's wrong, and just say, oh, well, I have these specific meshes and I'm just going to use whatever I can to actually achieve that result. And I don't know. I guess my point is it ends up being a trade-off all the time between like what do you want to show, what tech do you have, and how can you keep it small. So like, yeah, kind of a complex answer, but it's, yeah. So I wanted to go over some of the code, especially in like what the operators look like and the compiler, because it's not that terribly difficult. What's in here? So my font's probably a little small over here, but you can see stuff like there's the editor, and there's the 3D engine, Opus runtime, Rivet, there's a Rocket client, and then we have all these tiny libraries here, and then a C API over the synth. Yeah, Alcama says better be full generative, CSG, primitives, extrusions, voila. Yeah, if you have an artist that's comfortable with working with those, and usually would just get comfortable with that kind of stuff, then that ends up working really well. And also Dana Collins says you can use low-res meshes and use them as base control for more detailed messages also. I mean, absolutely. Like it's really about what you want to show and the tech you want to make, I think is really the only real answer. Because 64K is actually a lot of space if you're doing things generatively. And so then it's more about the tools to work with that kind of data. But it really depends on the kind of things you want to make. Okama says these days geometry is all gone in favor of remarching in distance field. Yes and no. Yes and no. Daniel Collin, indeed, which is cool in some sense, but also looks very similar these days. I definitely agree with that. But there's ways of getting around that. That's for another time. So these, you'll notice a lot of these look similar to the block diagram. In particular, I want to look at the Opus runtime. So here we have this is the export blob. This is what it actually looks like. We can deserialize that, for example. The serialization of the export blob is in Opus. The deserialization is in the Opus runtime, which makes sense. And then we have basic abstractions for, some of the 3D engine components. I think actually the engine folder that's in here isn't actually used anymore. I think that's the old engine that just kind of lingers. But I don't think it's used anymore because I think everything is moved to the Opus runtime now. Stuff for matrix, some basic primitives, render targets, shaders, some basic sync stuff, basically sync tracks. We do have stuff for doing textures here, but I think it's only really used to build render targets. So if you'd expect, there's a custom vec in here because we can't have some alloc stuff. What's that to do? Oh yeah, that's fine. And the bytecode is where things start to get a bit interesting here. I'll call it hint. Yep. So the bytecode, this is basically, we have some constants just for wrap modes, for example, but then there's just all these different ops. And this is as basic as it gets. Probably should have put these in enum and then have them have their values be enumerated like that, but this is just the way I ended up doing it. Subroutine start, call ret. These are basically blocked by the kind of things that they would do. So there's also not necessarily a one-to-one correspondence between the operator and the tool and the actual bytecode that makes. It's quite often that I'll take an operator in the tool and I'll split it into 3 or 4 different opcodes, because the JIT will want to do the bytecode is just this like linear stream of code, whereas the operator graphs had like some hierarchy in like how it could jump around and have things to be scoped. But we lose all that hierarchy. We lose all that higher information, just have the linear stream of instructions in the bytecode. So there's a lot of times when like we had to push something onto a stack and then run some stuff and then pop something off the stack. And so in the bytecode, that's actually two different operators, even though it was one operator, or like two different instructions where it was one operator in the tool. So you see a lot of like load var, store var, push var, pop var. Let's see if I can find another example of that. Yeah, like op dep test start and end, func start, func end, that kind of stuff. And especially with a lot of these control ones with like functions. Oh wait, that's actually blend function, but subroutine call ret. Yeah, we have like a subroutine start opcode, which is used to mark the beginning of in the x86 code where a subroutine starts, and then that's used to fix up some addresses later in the JIT. So anyway, but all these are fairly straightforward. We can like push and pop different kind of matrices, like the world and the view matrices. I also have separate operators for like all the matrix stuff, even though I probably should just have the same bytecode for those, but then have an argument. So there's a lot of those kind of refactorings that I think I want to do, but it really doesn't affect the size much, and it's more this way just because I ended up adding things all the time and not changing stuff so much, but probably end up changing that. I mean, this stuff changes fairly often, like as actually, that's not necessarily true. Like this stuff isn't a constant when we're making a demo, but it's one of the things that doesn't change that much, I guess I should say. Like we can, like the bytecode evolves, but it doesn't evolve as much as our content, if that makes sense. And of course, it's all a work in progress. And then of course we have these other operators just for arithmetic stuff. So I mean, in terms of a bytecode, this should be pretty straightforward, except that it might be kind of funny to see all this GL specific stuff in here. But I mean, that is what this particular bytecode is designed to do, is sort of wrangle some GL calls, really. So that's the bytecode. It just has a bunch of these things. And then this is like the interchange format for the bytecode. So we have then the operators that get compiled to this, the operator graphs that get compiled to this, and then of course some metadata that goes with it. And then we have the JIT that turns this into x86. And the JIT is actually a bit simpler, so I think I'll go over that next. So that's in this JIT folder here. Now there's a few pieces to this. So if we look at context, context is the actual like context object that holds all the state that the bytecode modifies over time. So for example, it has a pointer to where the variables are stored. It has a current world matrix and a stack for preserving those if it needs to push and pop those. Same with view. Has a constant projection matrix just because I guess I haven't had to change that at runtime yet. Same thing for frame buffers, same thing for GPU programs, texture units, all that stuff. Has a big old like string table that it uses for uniforms. It has a pointer to the asset manager, or a reference to it, sorry. Pointer depending on your depending on which side you're looking at. And then a bunch of stuff like the random seed, more stacks, and then some like static geometry objects. And that's pretty much all that is. And then of course when we create a context, we have to make variable storage and all that stuff. And we put in some hard-coded variables and also the sync variables. And then just initialize all this stuff to default stuff. Really not that exciting, but that's kind of need to see that first. Then we have this JIT function module. And this JIT function here, this is kind of the idea, is that we have a JIT function and then it has a run function. So the JIT function is just a function that you can run, really, and you have to give it a context. But the idea is you use a JIT function builder to actually build the function, and then you get the JIT function out of it, which is basically a pointer. So you can see here, for example, we get we take its own memory, which is where we've dumped all this x86 code, and we just convert that into this function of this form. So the context here is the context object, and then we also stick the variables in here because the JITted code will just reference those directly. And then we just call it. So that's kind of the idea there. Move away 000. It's pretty cool to see no std Rust, pretty similar to regular Rust. Yeah, it really doesn't change that much. I mean, there's some more unsafe stuff and some pointers, but it's really pretty straightforward. It's a bit longer than the equivalent C in a lot of cases, though, but it's not that bad. I mean, you still get a lot of like the ownership and borrowing, so we just kind of take advantage of that, but it's not that bad. Here you can also see that there's some Windows versus Unix specific stuff. So we use like virtual alloc, virtual free, and also mmap and munmap. We can't use like heap alloc and heap free or malloc and free for these because they actually have to be, we have to alloc whole pages when we're doing a JIT because we have to make this. So basically the idea behind the JIT is we basically just have a buffer. And then we just dump a bunch of data into that buffer, which ends up being x86 instructions. And then we take that buffer that we dumped all that stuff into, and then we mark it as executable. And in order to mark regions of memory as executable, they have to be page aligned. And then we mark whole pages. So that's why we use these functions like virtual alloc and munmap, is because we're actually allocating whole pages rather than just some chunk of memory. So that's like the first JIT specific thing that you actually see here. So the JIT function builder here really just will allocate some memory, just a big piece of memory, really. In this case, it's 2,048 pages by, of course, 4,096 bytes per page. So I believe this ends up being, I think it's 8 megs off the top of my head. I don't really remember. But it just allocates a big buffer, and we never get to that size. So it's like way bigger than any of our compiled code will ever be. But we allocate it up front rather than growing that memory because, again, because the memory protection, we need it to all be page aligned. And of course, we could make like a page aligned vector, but it's easier to just say, okay, just give me a big buffer, and that's fine. So the JIT function builder will first just allocate some memory. You can ignore this to-do comment here. And again, that's just basically page line memory. We also allocate everything as readable and writable, not as executable yet. We make it readable and writable, and then we write everything, and then we're going to make it executable. So it technically wouldn't also doesn't have to be readable, but I think when I was debugging, it was a bit easier to make that readable as well. And then we're going to fill that buffer with stuff, and then we're going to call this toJIT function, which is then going to change the memory protection. It also clears cache because this actually shouldn't matter. This would only matter if we don't reallocate the memory every time, but we do. But it's a good idea anyway to just clear the cache in case it had the same thing or whatever. It felt like a good idea to do it, even though I don't actually think it's necessary. But the idea is we just change the protection, really clear the cache, and then we're done. Then that memory is suddenly executable code. And of course, there's a Unix version, and then the Windows version is basically the same. Except we use mprotect on Mac and then virtual protect on Windows. Super simple. You can also see that we have things to get the memory pointer and then the offset, and those are used while JITting, which I'll get to in a second. But this JIT function thing is meant to sort of be agnostic. Like, it doesn't really have anything to do with the bytecode itself, except that it also has a lot of these functions that basically just serialize assembled instructions. So we don't want to have a full x86 assembler because that's going to be a lot of code. So instead what I do is I just opt in to have a bunch of functions that just like assemble the actual instructions that we'll actually use in the JIT. And a lot of these are really low level. Like, it's kind of funny to just see like move EAX with immediate 32. But this ends up working, excuse me, this ends up working actually really well. So other than the fact that what instructions are actually supported here, like there's a ton of holes, doesn't support like hardly anything compared to what x86 supports. But it supports exactly what we need for the JIT. So other than the fact that this list of functions is driven by what the implementations of the opcodes in the JIT need, it's really just like, at this level, it doesn't know about the opcodes other than it exposes these things that they need. This is just dealing with basically raw x86. So there's just hard-coded bytes for all these. Call will do things like you give it the destination, it will actually figure out the offset because that's relative, stuff like that. And the way I found these out, of course, you just go on any like online assembler or whatever and just type in the instruction you need. So like when I'm implementing the opcodes in the JIT, I'm basically, okay, this is the x86 that I think I want. And I just kind of write that out in like a scratch buffer. And then I go and for each instruction that I use, each form of the instruction, I go in and find some like online disassembler. And I just say, okay, what does the disassembly look like? Oh, it's these bytes. And then I turn those into these instructions here. So it's that simple, right? And so that's our whole like JIT function here. And that's most of the low-level details, although there's some stack alignment stuff that the actual JIT has to deal with. So yeah, so that's sort of the stuff that's agnostic to our opcodes. Then if I go to the module here in the JIT module, this is where it all kind of comes together for the JIT. Foodwork says remove the protection. The protection is in the DEP in Windows. I don't know what DEP stands for. Yeah, data execution prevention. Yes, exactly. So it's yeah, basically yes. Windows actually will give you, if you ask for memory that's readable, writable, and executable, it will give you that. At least it did in my tests, but I didn't want to risk it. It's usually a good idea to just ask for read write and then do the data and then protect it later, like changes protection so it's executable. But yeah, that's also why we have to allocate page aligned memory, is because those protection settings are per page, not just per random memory block. And that's because they actually have to have some hardware support in order to be implemented properly. So this is the actual JIT that will take bytecode from the tool and give you a JIT function. So what I do is I take the JIT function builder, I make one of those, and then I have some tables here that are basically used for stuff that we're going to fix up in the x86 stream later. So for example, if you want to call a function, we need to insert a dummy call, because like we need to know, if you're going to call a function, we need to know where the JITted code for that function is going to be in memory, but we don't know that until we've JITted it, right? So we're just going to JIT all the bytecode, and we're going to add a bunch of like dummy calls and stuff, and then later we're going to keep a table of where those dummy calls were and what they pointed to, and then we're going to go and fill in those addresses later. This is really common when you're talking about linkers and loaders generally. They will do this as well. They're called relocations or fix-ups. In this case, I call them fix-ups. And then some other tables that those would actually need to use as well. And then we just literally take the linear stream and we just basically translate each of the ops in our bytecode into the equivalent x86. And it's a pretty linear transform minus the fix-ups. It's all been kind of designed to be, for this passage, just be as simple as possible. So we do our function prologue, and then you can see I have some comments here so one of the things about the different ABIs versus Windows and OS X, on Windows, the Win32 ABI states that whenever you make I may be a little bit wrong about this because there's a small correctness detail here, but it's either whenever you call a function or when you enter a function. I think it's whenever you call a function. The stack pointer has to be aligned on a 4-byte boundary, right? So like if you take the stack pointer and you AND it with all Fs and then a C at the end, that will be the value of that operation will give you the same thing as the original value, if that makes sense. Like those bits have to be cleared. So that's on Win32, but on OS X it's actually a little bit more strict. That when you call a function, it's assumed that the stack pointer is 16-byte aligned, not 8-byte aligned, or sorry, not 4-byte aligned. And that has to do with was it MMX or was it one of the other extended instruction sets? I think it's MMX, because the MMX values in memory have to be aligned to 16 bytes. In Windows, it will actually just adjust the stack pointer first and then allocate stuff. But yeah, just has to do with differences in the ABI. Of course, the interesting thing about that is that since on OS X it's 16 bytes, on Windows it's 4 bytes, you can basically just do 16 bytes all the time. Make sure your stack is always 16-byte aligned whenever you do a call instruction, and then everything just works out on both platforms. So yeah, so that's why I put this here. And also, there were a couple times where I would change the prologue, for example. Like I didn't initially have push EDI and push these values first. So this comment at that point was 8 byte align, and then it was more necessary that I knew that. But the idea is that when I actually, Daniel Collins says SC, yeah, that's the one. It's SC that actually has that constraint. Yeah, so like in the actual ABI, it's necessary to have the stack pointer aligned to something when you're doing calls, but I add the extra caveat that we make sure the stack is always aligned between actual opcodes. And that's a little bit more strict, but it makes it way easier to keep track of when I'm actually going in here and changing the operators. And we'll see later in some of this code how simple that actually ends up being. But yeah, it's really important. So the reason why we have to care about that, if we were just calling around in our own code, as long as the stack pointer is the same as it was when we came in our function, we're fine. But the issue is that a lot of these functions will call into other functions. So for example, a lot of these will call back into OpenGL functions, or they'll call back into, a lot of them are just implemented by pushing some stuff on the stack and then calling back into Rust. And then the Rust will go do stuff with like the 3D engine. All of that stuff needs to maintain this ABI restriction. So that's why that's really important. But other than that, like there's not really very many things that we actually have to think about here, other than some calling convention stuff, but that ends up being really straightforward. And in fact, I actually got a bit clever here, and the function that this generates is, I can't remember which calling conventions they were, but I think the functions, so the function that we generate is cdecal, but it calls into functions that I mark as std call. And the reason why I use different calling conventions is because they have different policies about whether the caller or the callee should clean up the stack after it's been called. And so because I don't want to generate any code that does stack cleanup, then I make sure that the functions we call into are a calling convention where the caller cleans up the stack, and the function that we generate has a calling convention that the callee will clean up the stack. Does that make sense? So we kind of get around doing all that work just by marking the calling conventions, which is kind of cute. But then after that, it's pretty straightforward. Unfortunately, some of the more complicated ones are actually at the beginning, but it's basically just adding tables. So you can see it's going to do a dummy call instruction here that it will then fix up later, which is why it's like marking this fix up thing here. But most of these functions are really, really basic. For example, like a lot of these just call back into Rust. So like translate X world will apply an X translation to the current world matrix in the context. So all we actually have to do is so I have these sub ESP and then add ESP, and this is to maintain stack alignment, because based on the size of the stuff that I push on the stack, so it looks like I'm going to push 12 bytes onto the stack, 8 bytes onto the stack, which is this one and then this one. Then I need it to be 16 byte aligned again, so that's why I do this. And then we just call back into Rust. And there's a bunch of Rust implementations of these functions down here. And then it's just basic Rust, right? So like we have a mutable reference to a context, which is really just a pointer at runtime. So we just have to make sure that pointer is where we expect it to be on the stack. And then some of these will like create matrices and set the view on the context, all that stuff. So most of the ops are implemented that way. But of course, there's a lot of them where we just like use the FPU stack directly for these kind of things. There's calls and returns that we have to do. And the functions, of course, have to be handled a bit specially. And yeah, but I mean, it's basically just taking the operators, deserializing the arguments from the bytecode stream, and then just translating that into basic x86 to basically do the same thing that opcode stream represented. There ends up, especially with all this like stack alignment stuff, there ends up being a lot of like extra x86 code than what we would necessarily need. So like if I did this in 2 passes, where like I generated like pseudo x86 and then had like a people optimizer that would go and like remove extra stack alignment and that kind of stuff, we would generate smaller x86 code. But the code size here is just so ridiculously small, and it ends up being just super fast anyway. That's just not a problem. Alternatively, we also could have just interpreted the bytecode, and while that would have been like an order of magnitude or two slower, it would have been, I don't know. I don't think it would have been that much easier. And this was a lot more fun for me to do because it was kind of a learning experience as well. But it ends up being pretty straightforward. And then, of course, the push var, for example, doesn't call back into Rust because we just do some particular, like we look up the variable index and then we do implement the instructions for that. There are some of the control flow ones that are a little bit more fun. So like the repeat stuff and how we generate that. But most of it was just like, okay, how could this work? I'll just write it in x86. Okay, it works on my online disassembler. Let's translate it. So it's pretty fun to write. Fuborg, how did you figure out or debug subtle issues like alignments, or are there things well known documented? So that's a good question. In particular, the alignment thing did actually give me trouble, and that was one thing where it would work half the time and then half the time it wouldn't, because like I just went for it and I knew about like the 4-byte alignment from Win32 because I did that a long time ago, and I just assumed it was the same for OS X. And so I just went for it, and then it worked until I started calling back into Rust, and like I would print stuff, and sometimes it would work and sometimes it wouldn't, and I didn't know why. I ended up just asking on the Rust forums in that case, actually, and someone just was like, "Oh yeah, that's part of the ABI. It needs to be stack aligned." Like the information's out there, and generally, if you look up the ABI documentation, you'll find all of it. Agner Fog has a ton of information related to this stuff. But yeah, I think that was the only time where it was really problematic, and the rest was fairly straightforward. But that's because I have some experience with coding assembler, at least on Win32, and all that just was the same. I think the alignment was the only thing that threw me, and then of course the other thing was the memory protection, and that if you look up any tutorial on like how to do a JIT, it covers that. So that was the other thing. Because sometimes if you call malloc, it'll give you a page, and like if you call like mprotect and everything, it'll just work if that was page aligned, but then sometimes it won't, so it's kind of intermittent. But yeah, I think those are really the only two things that actually caused me any grief when doing this. And debugging it was pretty easy because I was doing this on OS X, and I was using, I think the tool is called Hopper, which was a pretty good debugger, because we could still build everything with the bug symbols in it, and it could disassemble the assembled code. And most of those issues were found out really early on as well. So like there's a lot of opcodes now, like 60 of them or something. But back when we had like 3 or 4, that's when we found these issues, and they never were a problem after that. So I'll comment, it's fun. I really thought modern OS introduced restrictions into jumping executing to allocated memory. Yeah, not a few. Just tell it to protect that stuff. So it is that simple. And I mean, this is a pretty basic JIT in terms of a JIT. Like it's not dynamically compiling different functions when they're needed, stuff like that. Of course, that would just be, calling a stub that would replace itself, and there's some other things there, but like it's pretty basic. We get some bytecode, and we return an address to a page that's executable. So this is really the product of a just try it mentality. Like, I wonder how this works. Let's try it. Oh, we ran into these 2 problems. Let's go ask online. So it's pretty fun. So then the last kind of really big piece of this puzzle is how do we get from a graph, like a grid of operators, into this data structure, and that's the compiler. So we go into Opus up here. This is where we have, okay, so first we want to go over the ops. So this is like string names for all the different operators that we have. We need like string names for all these because we're going to like serialize and deserialize a lot of this stuff. And this is before we had custom derive. So like now I could replace a lot of this with just stuff that like Serday uses, but that's not what we had there. Alkama says it's a lot of work there. Why not just doing a bytecode interpreter? Is it that faster? I would argue that it's not that much harder in this case. I think it's definitely an order of magnitude faster, but I wouldn't say that that's a good reason to do it. It was more that I wanted to do it because I thought it'd be cool. And I don't think it'd be that much harder in that case. because the interpreter would look a lot like the x86. And those like 3 files that I showed you is it. So I guess it's more work. I mean, you would either do an interpreter or you would do a translator and a jump. So, but I mean, it really was because it was more fun. I thought it'd be cooler. And it would be cooler. It wouldn't be that much harder. And it was really fun doing that. And it feels really cool to say, oh yeah, my demo tool has a jig compiler in it. So it's pretty fun. Especially in the demo scene. If it's going to be more fun, that's a great reason to do something. Yeah, Daniel Collin. So, anyway. And if you've never made a JIT before and you want to try it, that's all you have to do right there. So, that's kind of fun. Anyway, so this is the compiler itself. Actually, this isn't the compiler. This is the actual representation of the operators in memory as we're working with them in the project. I'll call my hair write assembly in hex. Writing assembly in hex would be really annoying, but I guess if you knew all the ASCII code, or all the ASCII codes. Wah wah. Okay, so this is the big enum with just all the different kinds of operators, right? So it's like there's a subroutine operator, and you'll notice that all the tag data on all these are just strings, and that's because like from the perspective of this structure, none of these strings really have any meaning. It's just a list of strings that can be modified, and these are the different expressions. It's not until this gets compiled until it matters that they're other things than strings, and we pull out the data from the strings there. Eventually, I will also probably have some metadata here, or actually it'll probably be in a little bit of a different structure that will say like, oh yeah, this is this kind of expression, so we need this kind of editor. But right now, we just have string editors for everything. Base effect. I saw some guy at Breakpoint doing it, coding with hex, and he was fast. Yeah, some of those guys are really good at that. Oh, comment I missed the call conventions because fun has limits. Damn, call, I bet you use punch cards also. Doc Retroid, yeah. 6510. Or do microcode assembler, one layer down. Yeah, so I mean, this is just like, should be basically what you expect to see in Rust. It's just this big enum of a bunch of different types with different strings. And I try to have like these new line separators between different like groups of these. And then of course we have like, you can create a new one from a string type, like a type name, and it'll give you these with default values. And that's used in the editor when you actually want to create one. You just give it a type name and it'll create the operator there. And you also notice that these operators here don't have positions because the operators themselves don't need to know about positions. It's only the compiler that needs to know about positions in order to see how the different operators will interact, but that's not really the operators' knowledge. They're stored in a hash map that knows about their positions, but the operators themselves don't need that. And then of course you can like get the type name. You can get an ordered list of expressions from those, and that's like used to show them in the tool. So it's pretty much just this one data structure and then all the code that just support code that other stuff that uses it needs. But at its heart, it's pretty basic. And of course we have expression names and all that stuff. Daniel Collin got all of Rust enums, yeah. And this one ends up pretty big, but it's one of those things that we change a tiny bit all the time. So it's not that bad. Then, of course, we have like serialization, deserialization. We also have export serialization. So there's a few to-dos in here, things that we can do to make this better, but this is the thing that actually makes the data blob, for example. And then we have the compiler, which is actually what I wanted to show. So the compiler, the main function it has is a function called compile, and it takes a position. It takes operators, which is a hash map from position to size or to operators. And then as a result, we'll either get a compiled program or a compile error, right? So it's like, I love the signature of this function because it is exactly like, this is exactly what you want to see for an interface to a compiler. Like, here's the only data you need. give me exactly what I wanted, or give me the exact reason why you couldn't give me that. So it's pretty nice. Daniel Collin might consider macros 1.1 for serialize. Do you mean the custom derived stuff? Because yeah, that could definitely be used now. But of course, this was made 6 months ago. So the compiler, the first thing it does is it takes the grid representation, and what it does is it turns it into an AST. And this is because the AST stuff, like, to have it in a grid is only really useful because it's convenient to work with and it's convenient to build an editor for. But it's still just a tree by the time we actually want to compile everything. So for example, if we look at this as like a tree, like this is a root, and then it has this as one of its children, and then that has this as one of its children, and so on and so forth, if that makes sense. So we're basically just going to turn it into that sort of deep AST. So that's what the parser is. And the parser will take, again, a master position and then these ops, and it will give you an AST or a compiler. You'll see these results of something in a compiler all the way through the compiler because I don't want the compiler to ever panic. So I'm pretty strict about that. But then it literally just parses an operator at a position, right? And then that will also parse its children. And then we also have to search the grid for subroutines in particular because those aren't actually reachable from the normal traversal of looking at everything's parents, or sorry, everything's children. And then of course we have, we want functions in a deterministic order so that we can have a test suite for these. So there's a compiler test suite of a bunch of different things. Basically, you just give it a master position and some operators, and then we get either a compiler that was expected or we get a list of ops. So these tests are pretty nice. And then, yeah, that'll give us a root node and then a list of subroutines. And this parse op at will literally just like parse an operator, and then that, depending on the operator, will also parse its children, or the stuff below that, but that's kind of up to the operator to, or actually, I don't think that's up to the operator here to do that, but when we do later compile passes, each operator needs to process its children at different points within the operator, if that makes sense. So for example, it needs to emit some bytecode, process its children, emit some other bytecode, so we have to do some stuff there. But at this stage, we also take all of the strings that were the expressions, and then we parse those into type data. So for example, if in this case we have a depth test operator that will either be true or false, and we need to parse a Boolean value. So we either, like, this is literally the word true or the word false, and then that becomes true or false in that case. So after this, we've done some, basically we have a very simply typed AST after this, where like all the expressions have been converted into, yeah, this is what the AST looks like. In some cases, some of this is still string data, like the subroutine still needs the name of the subroutine, same with args and which subroutine you're calling. But then a lot of these things will have expression values, or like the translate stuff will need to know which matrix it's operating on, all that stuff. So we've basically, this is the typed sort of version of this. I'll comment, do you bother eliminating dead code and assets? I think I eliminate functions that aren't called, and I think that's it for now. And of course I dedupe things. But yeah, I don't think there's much interesting stuff that happens on that level because the data structures don't end up being that redundant in our case. So I think there's some room for improvement there, but haven't needed it quite yet. So that's the like parsing phase, and then we'll get this node. And so each node has like typed data, but it also has a position and then children. And the position, again, is never really used. Like the position is only relevant when building this structure, but it's also relevant when you want to report errors, because later if we find a compile error at a specific node in this AST, we want to actually be able to tell the editor where that was. And that's what allows us to, like, if we make something that doesn't work, it allows us to like turn this red because it knows where that error occurred. So that's why we still have the position here. But other than that, it's just some, yeah, crazy simple structure here. And also, I was talking earlier about how I want to be able to have these, like, you can drag these out and then they'll have width, and then they will have multiple children. You see what I mean? The only difference is in the parser then, like of course in the UI, but then in the parser, where, like, in fact, this data structure here even already supports having multiple children and visiting all the children in order. So then it's just a matter of parsing that from the grid into this structure, and everything else should just work. Like, this is, after this point, the fact that it was a grid doesn't matter, and it's a like classic AST, which is good. That's the kind of stuff that we want to be working with then. So then we'll create a compiler context, and this just has a bunch of like extra stuff on it, ref counts for things and all that stuff, just because we're going to do a bunch of passes over the AST and fill in a lot of these structures. So for example, we go and find all the subroutines, and that may do some other things as well. Yeah, we go check its args, all the arguments of all the subroutines. We do some stuff for global variables. We do some stuff to check variable scopes. We do some stuff to check references for different sync tracks. We do some ref counting for variables, and then we sort them based on usage, which is kind of a cheap register allocation strategy where the most used one should be the lower value. That's to make things compress well, but I don't have any data on how effective that was. That was just something I thought, oh, that's kind of neat that I could do that. But honestly, it wasn't guided by any actual data. It was just something that I thought could be cool. Of course, we also override that a bit because like the first variables are always these hard-coded ones. And then there's the variables that were actually made in the program, and then there's the sync variables after that. Then we do some more passes, like we check some additional metadata for render targets, render target bindings, programs and uniforms as well. And then we run a code gen visitor on all of that, which will basically generate all of the code for all the individual operators. And then we put in an end opcode, and then we generate code for all the subroutines. So like you can basically think of the bytecode itself, or of like the bytecode stream that comes out as a bunch of functions, and then the first one is the entry point, and the other ones are other subroutines with some additional operators to mark where subroutines start in the bytecode stream. And then we serialize that, and then we have a compiled program. So it's pretty classic compiler, I think, and which is one of the things I really like about it. Like, I'm the kind of guy that really likes things to be done in a really straightforward way, and I don't like a lot of surprises in these kind of things, and I want each of these bits individually to be kind of how you would expect them to work, because then like you don't have these crazy bugs that are really hard to find because you're not really doing anything crazy. You're just putting together predictable things in the right way, in the way that you kind of expect, and then things kind of work out. So I think that's pretty fun. Thanks, Colin. Thanks, Alkama. And then of course these visitors here are pretty much what you expect. They're a bit verbose because like a lot of them will go over like a bunch of different node types. And a lot of them rely on this compiler context being kind of an aggregate for a lot of different tables, for example. But it ends up being pretty comfortable. There's a couple longer ones here, like when we do variable scope visitors, we actually have to go over all the different node types because we need to know, for example, like if we have, what am I trying to say? Like a local declaration, we need to add that to some of the tables and do some scoping stuff, and then visit the children and then pop that scope. So we have to do that kind of stuff, even though a lot of it ends up just being the same. And there's a couple of those longer ones. The code gen one is probably kind of interesting. Oh, yeah, also with like render targets, we check like that render targets are all unique. We check that all of them have like data that makes sense. We also, on the render target bindings, we check that they bound to render targets that exist. We check that things like when you specify render target binding, you specify like which color buffer you're binding to, or if you're binding to a depth buffer. And this will check that, okay, the render target that you're binding to has a depth buffer, or that you didn't go out of bounds on the index of the color buffer. And it's really cool that actually like those kind of little type checks in this language are actually super nice, because those are the things like if you start taking buffers and like binding them to other things to test stuff out, it's really good to know if that doesn't work, it's really good to know why. And having a really strict language like this where we can actually check this stuff at compile time is super useful for catching those errors really early. So I'm really happy that we have that. We do, what is uniform visitor? Oh yeah, uniform. We have to visit the uniforms for similar reasons, because you can have a uniform that ends up being a texture from a render target, for example. So that needs to do a lot of the similar checks. And then the code gen visitor is this last one, and this is like one again, like a really simple pass, because it's like, for example, global decal. We're going to get the variable index. We use unwrap here because we assume that earlier passes kind of took care of some of this stuff. We get the variable index. We emit the expression that will evaluate to the value of this thing, and then we push the store variable opcode, and then we visit the children. So it's pretty cool. Also, there must be a fun expression solver too for those math and input fields. So that's done in two places. That's done in the parser, which uses nom down here to parse bin ops here. And also, yeah, so here we have parse expression. And then we have sort of the classic ways that you might actually build up expressions. But so like the operator precedence and everything, that's all done in the parser, so that things won't parse if it doesn't actually make sense. And that we'll get an AST, like we'll get expression nodes in our AST. I don't think I showed that part, that we have an expression structure here with like const values or random values, varref, syncref, unary operators or binary operators with some sub expressions. We rely on the parser to actually give us correct data there. There's a couple fun things about how like it parses like bin ops, because you parse the left side and then you parse a bunch of right sides as an operator, and then the right side pairs, and then you kind of reduce those into a tree. So there's some fun stuff there, but generally it's all at this parser level, and then that's a couple hundred lines. But then the code gen ends up being super simple because we know that all that's correct. So the code gen for an expression, which is this emit thing here, is this. That's the whole thing. Which is again kind of what you'd expect, because the at runtime the floating point expressions are all like, we use the FPU stack for that, which is already stack based. So all we have to do is push the stuff that we like, for example, the unary op. We push whatever the child expression, the sub expression here is. We emit whatever the opcode is to generate those, and then after that runs, we will have expected that its result was on the stack. So then we can just emit one of these opcodes that will then operate on that top thing in the stack. So again, pretty standard stuff here. Ends up being pretty good. I think I recently switched from using nom whenever I would do a lot of these kind of things to, I think it's called combine, which is another library in Rust that's not macro based, and ends up being, I think I prefer it a little bit more. Has some corner cases, or has a few less corner cases, and of course, since it's not macro based, the errors that you get from the compiler when you use it wrong are a bit more straightforward. So I might want to replace that, but no real need to do that. In the Virtual Boy emulator I'm working on, I recently swapped out nom for that. But that was because we had a couple cases where it was like the order in which you specified certain parts of the parser would actually matter, and it shouldn't have. So there are some kind of bugs there. But all in all, not too scary, I think. Move away 002. I've been a fan of Lollipop. / me Googles. Oh, it's an LR1 parser generator for Rust. Yeah, that one I hadn't heard of. I did use, I don't think it was this one, but there was another parser generator that I also used for Rust, and I can't remember what it was called, but it was like a long time ago, and it was Like I remember it not being very featureful, but I remember really liking it. It was I think it was called RustPeg actually, because it was partial expression grammars, I think it's called. It's kind of the same idea. But then of course libraries like this will be a bit like higher level and a bit slower at runtime, but it doesn't really matter. Like this whole compiler here, this is whenever I change anything in the editor, everything gets recompiled. So it goes through this whole thing and then it goes through the JIT. And that whole process, I haven't even measured it because it's just so fast all the time. Like I haven't at all felt any slowdowns in the tool other than making the intro do slow things. So like again, every one of these changes I'm making here, it's recompiling all the time. And when I hold undo like that, all those changes it recompiles. So that is just like not a problem for speed, which is really nice because then we can just sort of do things the way that we would normally do them and just not worry about that. Pests, I also haven't heard of that. It seems like Rust just has a lot of these ones that are pretty good. So far I've only used RustPeg, Combine, and Nom, and I think I like Combine the best of those. But anyway, I think 2.5 hours. This is a proper stream today. I think that's basically everything that I wanted to talk about and kind of show with this tool. I don't really think there's much I left out. Next week, what I want to do... Now I'm really glad I split this up because I was actually worried that I would go over this really fast. And then... Oh, excuse me. Like, I had the idea to split up so I would talk about the tool this week and then talk about Elysian in the tool next week. And I was worried that those would be too short, but now I'm actually really glad we did that. So, but if any of you guys ever catch me at demo party or basically anywhere and you want to see this stuff, do not be afraid to ask because I love talking about it. I love sharing it. And it's really fun. So cool. I'm glad you guys like the explanation as well. Also, if you want me to go into any more detail or are curious about different parts of it, go ahead and shoot me an email if you want or something, and we'll get that figured out. Trailer, it was really interesting to see a real JIT that wasn't that complex. I think that sentence sums it up. It's a real JIT that's not that complex. I think that's pretty accurate. I mean, it's a useful JIT in this very limited context, and so I'm pretty happy with it. So glad you think that's cool. Another thing, so last week's episode, I forgot to hit record, and so I ended up having to download, like the stream cut out halfway through, so I ended up having to download the two different halves from Twitch, and I went and tried to stitch them together today, and it looks like the first half has some audio sync issues. So like it goes in and out of sync, and I don't really know why that is. I did a couple test renders, and the one that I have now is about as good as I think it's going to get, so we're just going to have to deal with that. But I'm going to upload that, and this week I did remember to record, so I'm going to upload those as soon as possible. But Hardcore Head 87, still at about 10% understanding, but still cool. Yeah, I did skip over a lot of like the context and a lot of those kind of things. This is going to be one of those streams that's going to be probably a little more useful for people that are looking into doing similar things or already familiar with the demo scene to some degree. But I hope it'll be a cool resource to see how a tool works, because this is just one of many tools belonging to many groups. But I'm pretty happy with what we have here, so I think that's cool. But yeah, so I'll get these uploaded as soon as I can, and I'll probably publish. I'm gonna try to upload them both tonight, so I'll probably publish both of those tomorrow evening. Of course, you guys that watch the streams, not gonna matter much, but yeah, just a heads up. Other than that, again, emulator stream on Thursday, and another demo scene stream next week, where we will go over Elysian and show what that looks like in the tool and the different kinds of how the different scenes are made, because that's actually pretty cool. And like seeing like the triangle tunnels kind of has a fun breakdown, that kind of stuff I think will be really cool. Hardcore Head 87, I've been a developer for years, never seen anything about compilers and stuff, so interesting to see that side of things. Yeah, that's cool. That's always the stuff I wanted to get into when I learned programming. So I ended up kind of diving deep there. So design, cool. I'm starting to get a grasp of how it works now. That's awesome. It's also cool in the demo scene because there's a lot of guys that, like me, really like that intersection of things like graphics and sound and compilers. So that was another reason why I was so inspired by like Looney's tool and why I wanted to take that approach, is because it kind of had that intersection. It's just three kind of technologies I think are really cool. One more thing, there's a discussion that came up on one of the videos so usually when I release these, when I get these videos on YouTube and I get them published, I go onto like 5 different subreddits and post links there. And generally because I've gotten a lot of upvotes and because I haven't really heard anything otherwise, it seemed like people were pretty happy to see those updates. I think but it came up recently that a couple people seem to not like that very much. So I think what I'm going to do is this one I'm going to post again, because I don't think I've posted like any of these to /r demo scene. So I'm going to start posting a couple of those, but I think I'm going to start holding back, holding back a little on posting the other ones. And just post like whenever I do something new or whatever. Because I think at this point, since I'm using like the same subreddits to post these, I think like the people that are going to see these have probably already seen them in those subreddits, and probably already follow what I'm doing on other channels. So I'm gonna hold off on that. So if you guys were relying on those, let me know somehow, and then maybe I can keep doing them. But I'm gonna, I think you guys know where to find me, so it shouldn't be much of a problem. What else? Oh yeah, also part of that discussion was, so this has come up a few different times where people are just generally talking about like how live streaming is a really bad format to spread information. And I think that sentence sucks. Like, first of all, I know that this format is really polarizing. Like certain people really want to learn from videos rather than learning from text. But at the same time, like videos are really bad for like random access or like going back and changing later. And then there's also that whole other side, which is where like streaming is really cool because it's not just like, here's 10 things to learn. It's like, here's kind of an interaction kind of thing. And that's why I really want to do it. So like, this is the content I want to make, and I don't plan on changing the format, but it has come up that that's the case. And one of the things that like, it's not the best content for some people, and I get that, but I'm not planning on changing on what I'm doing just because this is a format that works for me to produce. However, one of the things that came up is that a couple of people were talking about like, if you took the same videos that you already had and just cut them down to like a 10-minute format that showed the highlights, that could be a lot more useful for some people. And I didn't think that was a terrible idea. Now, I don't plan to do that, but if someone wants to do like video editing or something and would like to kind of take on that task, again, no pressure on anyone just because this is something that came up, I'd be really interested in supporting that. But again, this is, as far as what I'm already doing, I don't plan to do anymore. But yeah, just saying like that did come up. And of course, my response to that is I'm not going to do that. But if someone else wants to, I'd be happy to share like the original versions of my content to make that happen. So. Yeah, Colin, I think this format is great. Don't change. Thanks, appreciate it. Base effect indeed. So design me too. Don't change it. So you see, we considered 10 to 15 minutes tops at university, but I guess this is a different thing. Yeah, this is pretty different. I think the format is perfect. Yeah, so that's also what I kind of said in that discussion on Reddit as well. I can post the links to it. Like that was my point, is that like this is working for some people, and I think honestly the thing came up more of as someone was annoyed to see my links in 5 of his subreddits every week. You know what I mean? So I think the context is a bit important there as well. Anyway, I can share that because I don't want to single the comment out or whatever, but I just kind of want to give you guys the context because I thought it was like really fair points. But again, like I think this is working for. It's definitely working for me, and it seems to be working for like the core audience that I have, which is then we're good. But there was that thing where it's like, if it was possible for me to do like 10-minute versions of the content I'm already producing, and someone else was willing to make that happen, then I'd be on board. But I'm not going to change anything that I'm doing. anyway, just wanted to bring that up in case anyone might be interested in that. But so anyway, thanks again, guys, for watching. I'm really glad you guys liked the stream. This stream in particular. I'm looking forward to sharing more of these tools, and after revision, I hope to open source these, not in a way that I want to make them easy for other people to use, but as a resource that people can actually look at. So I think that could be cool. And I also want to get to the point where we use these streams where I just make stuff. I think that'll be really fun. I'll come. I'm gonna buy you a beer at revision. That sounds great. Try later. Yeah, no problem. I'll come. Colin. Really glad you guys are still liking the stream. So you see, keep it up, please. Thanks. Will do. Surveil Super Nintendo stream soon. Yes, I will definitely be going. So I think it was in 2 or 3 weeks that I wanted to go over that stuff. 2 or 3 weeks. Must have been. Because I wanted to go over Elysian in this tool. But after that, then I've basically shown all the 64K tooling that we have. So I wanted to use some more weeks going over tooling, and then I think Super Nintendo stuff is next. Base Effect, thanks, man. Fuborg, did you make a compiler for Super Nintendo 2? Yes and no. I do have a bytecode for that and a bytecode interpreter that runs on the Super Nintendo that makes my Super Nintendo demos work. But I didn't make a compiler per se. So there, Surveil is linking one of the demos. Yeah, Smash It is the one that's all used for. So, but we can talk about that later. So I think that'll be in 2 weeks is when we start going over that tooling. Although I think in 2 weeks I think I was going to go over the audio part. So maybe it was 3 or 4 weeks. I don't remember. In a couple weeks we'll talk about that. So that'll be fun. But yeah, anyway, thanks again, guys, a lot. This is really cool, and I'll see you later.